Yesterday morning, October 29th, 2025, at precisely 11:47 Coordinated Universal Time, an event unfolded that remained completely unseen by us. 3I Atlas, the interstellar visitor that has enthralled astronomers since July, reached its closest point to our Sun. This moment, known as perihelion, occurred with a separation of 203 million kilometers. For the first and only time on its voyage through our solar system, it vanished entirely from Earth's view, hidden behind our star like a card player shielding their hand. Now, most comets have no agency. They are prisoners of gravity, their paths predictable and calculable down to the second. But what if this particular visitor was different? What if, during those crucial hours when we could not observe, during that perfect blackout when no telescope on Earth or in Earth orbit could track its movements, 3I Atlas did something no natural comet could possibly do? What if it executed a turn? Not a gradual drift, not a subtle shift, but a deliberate, precise maneuver, using the Sun's immense gravitational pull as a cosmic slingshot. This action could have redirected probes, perhaps dozens of them, not out into the void, but inwards, towards the inner planets, towards us. This is what we call the Oberth-maneuver. It's a technique we employ with our own spacecraft for maximum efficiency. By firing engines at the point of highest velocity during perihelion, you achieve the greatest return for your energy expenditure. Avi told us to anticipate this exact scenario. He warned that if 3I Atlas was anything other than a natural comet, yesterday would be the day it revealed itself. And now, as November dawns and our telescopes strain to reacquire the target, some are indeed detecting signals that defy projections, trajectories that have shifted, and objects that were not there before. This is no longer a drill. This is no longer speculation. This is the reality unfolding when a 7-billion-year-old visitor, originating from the direction of Sagittarius, from the very heart of the galactic center, decides that Earth warrants a closer examination. As November begins, and our telescopes painstakingly reacquire the target, some are now picking up signals that deviate dramatically from our projections. We're seeing trajectories that have inexplicably shifted, and detecting objects that were simply not present before. This is not a drill. This is no longer mere speculation. This is what transpires when a 7-billion-year-old visitor, hailing from the direction of Sagittarius, from the very core of our galaxy, decides that Earth itself is worthy of a more intimate inspection. The European Space Agency's Jupiter Icy Moons Explorer, JUICE, was the closest human-made object with an unobstructed view. It was 64 million kilometers away, still an immense distance, but in cosmic terms, practically a stone's throw. JUICE was not designed to study comets. Its mission is to explore Jupiter's moons, Ganymede, Europa, Callisto, in search of subsurface oceans and potentially habitable environments. However, on October 29th, mission controllers made a significant decision. They temporarily redirected its sophisticated instruments. They aimed to gather at least some data from perihelion, a record of 3I Atlas at its moment of peak solar heating. The initial data packets arrived 11 hours later, containing routine telemetry, compressed imagery, and crucial spectroscopic readings. The science team, gathered in Darmstadt, Germany, painstakingly processed this information overnight. It was then that a profound anomaly emerged. 3I Atlas was significantly brighter than predicted, not by a small margin, but by almost an entire magnitude. Now comets can indeed surprise us with their brilliance. Outgassing can surge unpredictably as volatile ices sublimate under intense solar radiation. Carbon dioxide, carbon monoxide, water, all transforming from solid to gas within minutes, creating those breathtaking tails and comas that define comets. The established models predicted 3I Atlas would reach a magnitude of 11.5 at perihelion. Yet, JUICE's photometry indicated a magnitude of 10.1. This translates to a brightness nearly 2.5 times greater than anticipated. However, brightness alone was not the sole puzzle. It was the distribution of this luminescence that proved truly astonishing. The glow surrounding 3I Atlas was far from symmetrical. Natural comets typically develop roughly spherical comas, perhaps elongated by solar winds into teardrop shapes, but fundamentally centered on the nucleus. What JUICE captured, however, presented a radically different picture. Multiple distinct bright spots, 7 separate luminous regions arranged in a clear pattern around the central body. Astonishingly, each of these regions exhibited its own unique spectral signature, its own distinct pattern of emissions. The JUICE data revealed something even more startling: motion. Specifically, relative motion. Between the time JUICE initiated its observation sequence and its conclusion, a span of 42 minutes, these bright spots had demonstrably moved. Their movement was not in the expected direction, nor did it follow the ballistic trajectory one would anticipate from ejected material. Instead, they were actively spreading out, diverging, and some were exhibiting distinct acceleration. Consider that for a moment. Natural processes do not accelerate in a vacuum. Once material is ejected from a comet, it adheres to Newton's laws. It coasts. While solar wind or radiation pressure might exert influence, these forces do not induce sudden accelerations hours after an initial outburst. Yet, here were 7 distinct objects, each estimated to be the size of a school bus based on their brightness and distance, demonstrating velocity changes that strongly suggested active propulsion. The initial report of these findings was classified within mere hours. This was not an act of concealment, but rather a restriction of information to the International Asteroid Warning Network, or IAWN, the designated body that coordinates global responses to potentially hazardous objects. By the evening of October 29th, 36 observatories across 4 continents had been alerted. Emergency observation protocols were immediately activated. Every telescope capable of slewing towards the solar region, every instrument equipped to detect objects in proximity to the Sun, was retasked for this critical observation. And it was at this point that a second set of anomalies began to emerge. NASA's Parker Solar Probe, a spacecraft designed to graze the Sun, was in the vicinity. While not positioned to image 3I Atlas directly, it was ideally situated to detect any radio emissions, any plasma interactions, or any unusual disturbances in the magnetic field. Parker's sophisticated instruments recorded a series of structured radio bursts that coincided precisely with the perihelion passage. These bursts were centered around 1.42 gigahertz, the hydrogen line, often referred to as the universal frequency. This is the specific wavelength at which hydrogen atoms naturally emit radiation, and crucially, it's the frequency that SETI researchers have monitored for decades, recognizing its potential significance for any technological civilization. The Parker data revealed distinct pulses, not random noise, and certainly not the sporadic emissions expected from natural plasma interactions. These were rhythmic, patterned, and repeated at intervals that followed a specific sequence: 3 seconds, then 5, then 8, then 13, then 21. Each pulse lasted precisely as long as its corresponding number indicated. And the pattern continued: 34 seconds, 55 seconds, 89 seconds. Some of you may already be recognizing this. This is the Fibonacci sequence. Each number is the sum of the 2 preceding it, one of the most iconic mathematical patterns found throughout nature, appearing in everything from the arrangement of flower petals and the spiral of galaxies to the breeding patterns of rabbits. It is a pattern that unequivocally signifies order, a clear announcement of mathematical awareness, and it was emanating from the direction of 3I Atlas at the exact moment of its perihelion passage. Let us be unequivocally clear about the implications of this discovery. The Fibonacci sequence does not manifest spontaneously in radio emissions. Solar flares do not count to 34. Plasma interactions do not perform addition. While natural processes can undoubtedly create patterns, they cannot generate mathematical sequences that inherently require memory, where each emission must recognize what preceded it and calculate what comes next. This is a clear demonstration of information theory. This is signal structure that unequivocally implies intent. The Parker data was immediately flagged for urgent review. By midnight Central European Time, copies had already been disseminated to the SETI Institute, the Galileo Project, and Harvard's esteemed astronomy department, where Avi and his team were already awake, deep in analysis, and sounding alarms that would largely go unheard by the rest of the world for another day. This morning, November 1st, the European Southern Observatory's Very Large Telescope in Chile successfully reacquired 3I Atlas. Having emerged from behind the sun, it was now visible in the pre-dawn sky for observers in the southern hemisphere. The VLT stands as one of the most powerful ground-based optical telescopes globally, capable of resolving details that would be impossible for lesser instruments. And what it observed corroborated the JUICE findings. 3I Atlas was no longer solitary. The main nucleus, the estimated 5 to 20 kilometer wide body we've tracked since July, remained intact and was still following a path closely aligned with its predicted trajectory. However, surrounding it, spreading outwards in what could only be described as a meticulously organized formation, were the 7 objects initially detected by JUICE. These objects were no longer clustered. They had separated, each now millions of kilometers distant from the parent body, each charting its own independent course. Alarmingly, 3 of these objects were not following paths that would lead them out of the solar system. They were decelerating, performing what aerospace engineers term a retrograde burn, firing their propulsion systems against their direction of motion to shed velocity. When their new trajectories were calculated, when the complex orbital mechanics were solved and projections were run, all pointed towards a single, startling destination: Earth. The date for closest approach began to repeatedly appear in the calculations. December 19th, 2025. Precisely 50 days from now. It is not the main body of 3I Atlas that will pass us at its projected distance of 270 million kilometers, far beyond any possibility of interaction. Instead, it is the probes, the 7 objects that detached at perihelion, 3 of which will arrive dramatically closer. Current estimates place them within 10 million kilometers of Earth. That's less than 1/15 the distance to the Sun, and astonishingly, inside the orbit of our own moon by a factor of 25. And here is where the situation transitions from fascinating to truly terrifying. These probes are colossal. JUICE's initial photometry suggested each one possesses a diameter of at least 30 meters. This is larger than any satellite humanity has ever launched, and significantly larger than the individual modules of the International Space Station. Furthermore, they are not tumbling randomly, as one might expect from debris or fragments. They are oriented, stabilized, each one precisely pointing in a specific direction as it travels, exhibiting what is known as 3-axis attitude control, the same sophisticated stabilization system employed on our most advanced spacecraft. How do we know this? Because they are reflecting sunlight in remarkably predictable patterns. When an object tumbles uncontrollably, its brightness fluctuates chaotically as different surfaces intermittently catch the light. Conversely, when an object maintains a stable orientation, its brightness remains steady or varies in predictable, regular cycles. The VLT photometry revealed periodic variations with cycles of exactly 16.2 hours. This is the identical rotation period that 3I Atlas exhibited. It is as if whatever detached from the parent body carried its spin with it, maintaining synchronization even after separation. This is not speculation. This is not hysteria. These are meticulously gathered measurements from multiple independent observatories, utilizing distinct instruments and methodologies, all converging on the same undeniable conclusion. Something occurred at perihelion, something entirely inconsistent with the behavior of natural comets. And now, as November progresses and our tracking capabilities improve with each passing night, we are compelled to confront possibilities that most scientists have spent their entire careers dismissing. The International Asteroid Warning Network convened its first emergency session since its inception on November 2nd. Representatives from NASA, ESA, Roscosmos, JAXA, CNSA, every major space agency, alongside astronomical societies from 37 countries participated. The meeting was conducted behind closed doors, yet the agenda leaked within hours. Item 1. Confirm the trajectories of all 7 objects. Item 2. Assess the probability of natural versus artificial origin. Item 3. Determine the Earth impact risk. Item 4. Establish communication protocols. Item 5. Authorize defensive measures. It was this final item, defensive measures, that immediately ignited headlines, appearing in multiple leaked documents. While no official statements have been made regarding the precise meaning of this phrase, the implications are starkly clear. If an object is approaching Earth, and we cannot be certain of its intentions, we must have options. Options for observation, certainly, but also options for interception, deflection, and even destruction if deemed absolutely necessary. The United States Space Force, the newest and perhaps most controversial branch of the American military, has quietly begun activating its assets. Satellite tracking networks, normally dedicated to monitoring missile launches, are being repurposed to scrutinize the region of space where the 3I Atlas probes are currently traveling. Ground-based radar installations, the colossal phased array systems engineered to detect incoming ballistic threats, are being recalibrated to track objects millions of kilometers distant. And within classified facilities, engineers are engaged in complex simulations, running wargaming scenarios to determine if our most powerful rockets could intercept the probes before they reach us, and if our most potent weaponry could effectively neutralize them should they prove hostile. However, a profound paradox weighs heavily on the minds of scientists, keeping them awake at night. We do not wish to destroy them. Even if we possess the capability and absolute certainty of success, the desire to do so is absent. Because if these objects are indeed artificial, if they represent the first confirmed contact with extraterrestrial technology, their destruction would constitute the single most catastrophic mistake in human history. It would be a declaration to the galaxy that we are violent, paranoid beings who shoot first and ask questions never. We would be obliterating the very evidence needed to understand who sent them, why they are here, and what their purpose might be. And so, we wait. We watch. We meticulously track every kilometer of their approach. We direct every available instrument towards them. And we collect data, spectroscopy, photometry, radar returns as they draw closer, and radio monitoring across every conceivable frequency. We search for more signals, more patterns, more irrefutable evidence of intent. And we prepare, quietly and with profound reluctance, for the possibility that December 19th will be remembered not as a day of triumph, but as either the greatest day in human history or its final one. The probes are currently traversing space at an average speed of approximately 68 kilometers per second relative to the Sun. This is incredibly fast by human standards, yet remarkably slow for objects originating from interstellar space. 3I Atlas itself was clocked at a staggering 221,000 kilometers per hour at the time of its discovery. These probes have shed an enormous amount of velocity. The energy expenditure required for such deceleration is nothing short of staggering. We can calculate it. Mass multiplied by velocity squared, divided by 2. Even assuming the minimum possible mass based on their observed dimensions, we are looking at energy expenditures equivalent to multiple nuclear detonations per probe. This is not the result of outgassing. This is not the effect of solar wind. This is propulsion. This is fuel being consumed, reaction mass being expelled, engines firing with purpose in the cold, silent vacuum of space. And this leads us to the question that no one wishes to voice aloud, yet it preoccupies everyone's thoughts. If they possess sufficient fuel to decelerate, do they also possess enough to accelerate again? Are these probes on one-way missions, content to simply observe and relay information back? Or are they capable of further maneuvering, of entering Earth orbit, of landing, of executing whatever their ultimate mission entails? We do not know. And that, perhaps, is the most honest and most terrifying answer that science has ever been forced to provide. Decoding the maneuver. The sheer mathematical elegance of what transpired at perihelion is almost breathtaking in its starkness. When dealing with orbital mechanics on such grand scales, every numerical value tells a story, and the story these numbers tell is one that simply should not be possible for a natural celestial object. Let us meticulously examine precisely what would need to occur for these probes to reach Earth. On December 19th, 3I Atlas approached perihelion at a velocity of 68 kilometers per second. This velocity was primarily oriented in the direction that would carry it back out toward interstellar space, following the hyperbolic trajectory we have been tracking since July. To redirect even a minuscule fraction of this mass towards Earth necessitates a dramatic alteration of that velocity vector. It requires not merely slowing down, but rotating the direction of motion through an angle approaching 90 degrees. The energy cost associated with such a maneuver escalates exponentially with the square of the velocity change. And when one meticulously plugs in the numbers, accounting for the mass of these 30-meter probes and the requisite delta V, the result is one that would make even seasoned rocket scientists blanch. Each probe would need to carry a fuel mass equivalent to approximately 40% of its total launch mass. This calculation assumes a specific impulse comparable to our most advanced chemical rockets. If they are employing a more exotic propulsion system, such as nuclear thermal, fusion, or even antimatter, the ratios would undoubtedly change. However, the fundamental challenge remains immutable. One cannot defy the laws of physics. To decelerate and subsequently turn towards Earth requires either the carriage of impossibly large quantities of fuel or the utilization of propulsion technologies operating at efficiencies that we can currently barely conceive. Dr. Sarah Chen, from MIT's Department of Aeronautics, has meticulously performed these calculations, employing our most optimistic projections for advanced propulsion systems. Even under the assumption of a fusion drive operating at specific impulse values 10 times superior to anything humanity has yet achieved, the fuel requirements remain staggering. We are speaking of technology that represents either thousands of years of advancement beyond our current capabilities, or a fundamental breakthrough in physics that permits propulsion without the expulsion of reaction mass. Either of these possibilities is profoundly sobering, but here is where the situation becomes even more peculiar. Consider the precise timing of the separation event. If the objective is to release probes destined for targets within the inner solar system, perihelion is not merely convenient. It is the absolute optimal point. This is the Oberth effect in action. When an object is deeply situated within a gravitational well, moving at its maximum velocity, every unit of thrust generates amplified results. Firing engines at perihelion yields a greater change in orbital energy per unit of fuel than at any other juncture in its trajectory. This is a fundamental principle of orbital mechanics, something we have understood since Tsiolkovsky elucidated the rocket equation over a century ago. The fact that 3I Atlas executed this maneuver, if indeed that is what occurred, at the precise moment of maximum efficiency, strongly suggests deliberate planning. It indicates an understanding of the local gravitational environment. Natural comets do not wait for optimal moments, because natural comets lack goals. They are governed entirely by the forces of gravity and outgassing, neither of which possesses any awareness of efficiency, timing, or whether they are being observed. And we were not observing. That is the detail that persistently resurfaces, the detail that feels less like a coincidence and more like a calculated strategy with each passing day. Solar conjunction is a predictable event, calculable years in advance. When 3I Atlas was first discovered in July, orbital calculations immediately indicated it would pass behind the Sun from Earth's perspective in late October. This is a matter of celestial geometry, not conspiracy. However, the perihelion date landing squarely in the middle of that blackout window, a period when no telescope on Earth or in Earth orbit could directly observe it, when even our closest spacecraft could only capture fleeting glimpses from oblique angles. That timing is truly remarkable. Some scientists, the more cautious ones, those who have built their reputations on rigorous skepticism, argue for coincidence. Space is vast, they contend. Such alignments do occur. The fact that we were unable to observe does not automatically imply deception, and in a purely statistical sense, they are correct. But statistics and reality do not always align perfectly. Sometimes, the universe arranges itself in ways that strain credulity, and when those arrangements coincide with other anomalies, with Fibonacci radio pulses, with trajectory shifts, and with the observed separation of probes, the explanation of coincidence begins to feel less like scientific reasoning and more like wishful thinking. The reverse Oberth-maneuver, the intricate ballet of deceleration these probes had to perform to reach Earth, demanded more than just fuel. It required absolute precision. Imagine a controlled plunge into a gravitational abyss, where engines fire at precisely timed intervals, shedding speed just enough to wrench yourselves into an earthbound path. A timing error of mere seconds could send you millions of kilometers off course. A fractional deviation in engine thrust direction, and you'd find yourself in an entirely different orbit. The fact that three separate objects, three probes, all executed their burns with such pinpoint accuracy, converging on Earth within the same 24-hour window, points to a level of coordination that is simply astonishing. This suggests either pre-programmed directives, uploaded before their separation, or an active communication network, where they're constantly adjusting their trajectories based on shared data. Either scenario screams advanced technology, sophisticated computational power, state-of-the-art navigation systems, and unparalleled propulsion control. Ground-based radar won't offer reliable tracking until mid-November, when they finally cross Mars's orbit, close enough for their return signals to cut through the cosmic static. But optically, our view is improving by the day. Each night, as Earth's rotation brings new telescopes into alignment with the morning sky, astronomers meticulously refine their measurements. The probe's trajectories are being calculated with ever-increasing precision, and these calculations consistently converge on the same arrival window, December 18th through the 20th, depending on which probe you're tracking and which orbital data you trust. The closest approach distances also vary. Current best estimates place Probe 1, the designation given to the largest and brightest object, within 8.7 million kilometers of Earth. That's roughly 23 times the distance to the Moon. It's far enough to pose no collision risk, yet close enough for our most powerful telescopes to potentially resolve surface features. Probes 2 and 3 are predicted to pass at 9.2 and 10.1 million kilometers, respectively. As for the other 4 probes, those whose trajectories didn't beckon them towards Earth, they are charting entirely different courses. 2 appear to be heading for Venus, expected to arrive in early January. 1 is en route to Mars, embarking on a slower journey that won't see it reach its destination until March. And the 7th, the most elusive to track, seems to be venturing outward, towards Jupiter. Its trajectory eerily mirrors the path 3 Atlas itself will eventually take. This distribution is far from random. 7 probes, 7 distinct targets. The inner planets, the colossal gas giant, and 1 veering back into the deep void, perhaps tasked with relaying mission data back to its origin. This is precisely the pattern you'd expect from a survey mission, a scientific expedition meticulously designed to sample diverse environments during a single sweep of the solar system. We employ the same strategy with our own flyby missions. Voyager wasn't simply sent to Jupiter. It was engineered to visit multiple celestial bodies, maximizing scientific return from a single launch. If 3 Atlas is indeed a mothership, and these probes its sophisticated survey instruments, then their dispersal pattern unfolds with perfect strategic logic. But survey missions inherently imply curiosity, a deep-seated scientific interest, a drive to understand, to collect data, and to learn. This leads us to the question that permeates every conversation, every meeting, every encrypted exchange between observatories and space agencies. What exactly are they surveying? What do they seek to know? And most crucially, what will they do with the information once it's in hand? The peculiar nickel signature hasn't vanished. Spectroscopic observations from multiple facilities continue to reveal an anomalous emission line, nickel vapor in concentrations that defy any natural cometary composition. Nickel is abundant in the universe, certainly, but it almost invariably appears bound with iron in roughly equal proportions. That's the immutable law of cosmic chemistry. Nickel and iron forge together in the fiery hearts of massive stars, only to be ejected into space as a unified pair when those stars meet their explosive ends. Every meteorite we've ever analyzed, every asteroid we've sampled, bears witness to this iron-nickel ratio. It's always nickel and iron together, except in the case of 3 Atlas. The spectra reveal abundant nickel, yet virtually no iron. This isn't astronomy, it's metallurgy. It speaks of refining, of smelting, of industrial processes that meticulously separate elements based on their unique properties, rather than their natural cosmic abundance. While some geochemists have proposed highly speculative formation scenarios, invoking exotic stellar environments where natural fractionation might somehow isolate nickel from iron, these hypotheses demand conditions so specific, so astronomically improbable, that they border on special pleading. The most straightforward explanation, the one that aligns with the observed data without inventing new laws of physics, is that this nickel is not natural. It's manufactured. It's an alloy selected for properties we can only speculate about, perhaps unparalleled strength, exceptional conductivity, or remarkable resistance to radiation or thermal stress, precisely the characteristics you'd desire in a spacecraft's hull. Then there are the light curves. As the probes rotate, they reflect sunlight in patterns that betray their physical form. Natural celestial bodies, be they jagged rocks or icy conglomerates tumbling through space, produce irregular light curves, uneven, asymmetrical, chaotic. The 3 Atlas probes, however, exhibit light curves that appear meticulously engineered. They display regular variations in brightness, marked by sharp peaks and smooth troughs. This is precisely what you would anticipate from objects possessing geometric symmetry, perhaps elongated ellipsoids or perfect cylinders. These are shapes suggestive of deliberate design, not the haphazard outcomes of cosmic chance. Dr. James Robertson at Caltech has been meticulously analyzing these light curves. He has constructed intricate models, run countless simulations, attempting to match the observed brightness patterns with various assumed shapes. His most successful model, the one that most accurately replicates the observations, depicts the probes as cylindrical objects, measuring approximately 35 meters in length and 12 meters in diameter. That's the scale of the space shuttle, the dimensions of a Saturn V rocket's upper stage. Furthermore, the surface reflectivity indicates smooth exteriors, a stark contrast to the rough, porous textures characteristic of cometary fragments. Of course, this is not definitive proof. Science rarely deals in absolute proof. Instead, science thrives on evidence, on models that faithfully represent data, and on hypotheses that withstand rigorous testing. Yet, the evidence is accumulating, piece by painstaking piece, measurement by meticulous measurement. And the hypothesis that stands strongest, the one requiring the fewest improbable assumptions and the least speculative physics, is that these objects are not of natural origin. Defense planners, operating independently of the scientific community, are running their own simulations. Their conclusions are driven by a different set of priorities. They are not inquiring into what the probes are, but rather what they can do. How swiftly could they maneuver if they chose to? What reserves of delta V or change in velocity might they possess? Could they alter their course again, target different locations, or even enter Earth's atmosphere? The answers to these questions hinge on assumptions about their propulsion technology and fuel capacity, assumptions for which we have no verifiable data. However, the worst-case scenarios, the ones that keep military analysts vigilant in their secure facilities, involve probes with sufficient remaining propulsion authority to execute multiple significant trajectory modifications. If they can decelerate from interstellar speeds, what other capabilities might they possess? Could they match Earth's orbital velocity? Could they maintain proximity, pacing us at fixed distances for extended observation periods? Could they descend into our gravity well, targeting specific locations on the surface? These questions inevitably give rise to others, darker and more pressing. What kind of payload might they carry? Instruments, certainly. Cameras, spectrometers, sensors of types we can only begin to imagine. But what else? Communication equipment, presumably, to transmit their findings back to the mothership or beyond. Computational power, navigation systems, energy generation. And if they are capable of such precise maneuvers and controlled approaches, why not descent systems, landing gear, even surface mobility? This is the nebulous territory where science fiction converges with strategic contingency planning. We have no concrete evidence for any of this, but, crucially, we also have no evidence to the contrary. The probes are black boxes, both literally and figuratively. We can meticulously measure their orbits, their dimensions, and their reflected light. But we cannot peer inside. We cannot ascertain their intentions or their true capabilities until they choose to reveal them. And by that point, if those intentions are hostile, it may be tragically too late to mount an effective response. December 19th is 50 days away. That's the window we have to gather intelligence, to refine our understanding, and to formulate humanity's response to visitors we neither invited nor can afford to ignore. 50 days to transition from denial to acceptance, from skepticism to preparedness, from hoping for a natural explanation to planning for the distinct possibility that it is not. 50 days until we discover whether we are truly alone in the universe or merely a single data point in someone else's extensive survey mission. The direction of origin matters. In the unfathomable expanse of interstellar space, where distances dwarf human comprehension and stars are scattered like grains of sand across a cosmic desert, the direction from which something arrives tells its own compelling story. 3 Atlas did not emerge from just anywhere. It journeyed from Sagittarius, from the very heart of our galaxy, from the quadrant where our Milky Way's supermassive black hole lies hidden behind veils of dust and stellar fire. That particular region of the sky, that 30-degree arc dominating the southern celestial sphere, has held a profound significance for millennia. Ancient civilizations perceived an archer there, a centaur poised with bow drawn, aiming his arrow toward Scorpius, the scorpion. Greek mythology bestowed upon him the name Chiron, the wise centaur, revered as the teacher of heroes, the one who ultimately relinquished his immortality to escape unending suffering. The irony is not lost on astronomers who now observe an arrow originating from that precise celestial locus bearing down upon Earth. We have experienced cosmic projectiles before, asteroids and comets that instigated mass extinctions and irrevocably reshaped continents. Is history poised to repeat itself? But this time not by accident, but with deliberate intent. The galactic center itself resides within Sagittarius, a staggering 26,000 light-years away, yet optically obscured, concealed by dense interstellar dust lanes that block visible light while allowing infrared and radio waves to penetrate. Sagittarius is a star, the colossal black hole anchoring our galaxy's core, possessing a mass 4 million times that of our Sun. It is a gravitational behemoth, warping space-time around it so severely that stars orbit at speeds of thousands of kilometers per second, their paths contorted into tight ellipses by forces that would annihilate ordinary matter. Within the intensely dense stellar environment of the galactic bulge surrounding that black hole, stars are packed so closely that their separations are measured in light days, not light years. Interactions are commonplace. Close encounters, gravitational slingshots, stellar systems violently disrupted and reformed by the passage of neighboring stars. It is a region of extreme dynamism and violence, a stark contrast to the tranquil cosmic suburbs where our Sun peacefully resides. And it is from this very direction, from this crucible of stellar activity and extreme physics, that 3 Atlas emerged after an eons-long journey spanning billions of years. Statistical analyses consistently return to a haunting conclusion. When researchers meticulously trace the object's trajectory backward, accounting for galactic rotation, stellar motions, and gravitational influences from all known cosmic bodies, the origin point remains stubbornly fixed near the galactic center. Not pinpointed to a specific star, such precision is unattainable across such immense distances and timescales, but firmly within that general region, that volume of space where stellar density reaches its peak and exotic objects congregate. And then there is the other signal, the older one, the one that stubbornly resists explanation or oblivion, despite decades of concerted effort. On August 15, 1977, the Big Ear radio telescope in Ohio detected a signal of such extraordinary strength and such precise confinement to the hydrogen line frequency that the astronomer reviewing the data the following day scrawled, "Wow," in the margin of the printout. That exclamation of astonishment became its name, the WOW signal. It comprised 72 seconds of narrowband radio emission, originating from, you guessed it, Sagittarius. The same constellation, the same general region, 48 years prior. The Big Ear never detected it again. Subsequent observations yielded nothing. Decades of diligent searching in that particular patch of sky have uncovered only an unnerving silence. Skeptics have proposed a myriad of explanations, from orbiting satellites to passing comets to clandestine military transmissions. Yet, none of these explanations fully satisfy the anomaly. Satellites do not produce narrowband hydrogen line emissions. Comets do not generate radio signals powerful enough to register from interstellar distances. And the signal's frequency, 1.4242 gigahertz, is deliberately avoided by terrestrial broadcasters, a protected scientific band meticulously preserved by astronomers. Recent analysis by Antonio Paris suggested the signal could have originated from a comet, specifically Comet 266 PNP, which happened to be transiting that region of the sky in 1977. Comets can indeed emit radio radiation through processes involving their hydrogen clouds, but the specific details of the WOW signal don't quite align. The signal was far too intense, too focused, and too brief. Moreover, when other researchers scrutinized the orbital calculations for Paris's proposed comet, it was discovered that it wasn't actually in the correct position to have generated the observed signal. The mystery persists. Now we have 3 Atlas, another visitor hailing from Sagittarius. This one, however, carries not just radio signals, but a physical presence, tangible mass and velocity, and structures that bear unmistakable hallmarks of artificial construction. The connection feels too significant to dismiss. 2 anomalies, originating from the same celestial direction across a span of half a century. What are the odds? Astonishingly, we can actually calculate those odds. The galactic center occupies approximately 1% of the sky as viewed from Earth. If anomalies were to arrive from random directions, the probability of 2 independent events both originating from that mere 1% is 1 in 10,000. While not statistically impossible, it is certainly noteworthy. Compound this with the fact that both phenomena involve narrowband radio emissions, and the probability plummets further. Introduce the specific connection to the hydrogen line frequency, and you enter territory where coincidence begins to yield precariously to correlation. Some researchers are venturing even further, postulating that the WOW signal might have been an intentional beacon, a deliberate hailing frequency designed to capture our attention and announce an impending visitor. 48 years elapsed between the signal and the arrival. By human standards, that seems an immense duration. However, for interstellar travelers, for civilizations possessing the capability to traverse light years, such temporal scales may be quite routine. Imagine sending a signal ahead, providing local inhabitants with advance notice, and then arriving decades later to ascertain if anyone responded. It's precisely the strategy we ourselves would employ if we possessed such capabilities. The Voyager Golden Records, the messages encoded for extraterrestrial intelligence on our deep space probes, embody this very same principle. Hello, we are here. This is what we are like. We are coming your way, even if it takes us thousands of years. The mythological resonance runs even deeper than the astronomical. Sagittarius, the archer, the centaur, symbolizes the liminal space between the human and the animal, between civilization and untamed wilderness. In Greek tradition, centaurs were esteemed as guardians of knowledge, adept teachers of medicine, music, and warfare. They bridged disparate worlds, inhabiting the borders between the known and the unknown. Could this be the role 3 Atlas represents? A bridge, an intermediary connecting our isolated solar system to the vaster galactic community that may exist out there in the cosmic darkness. The constellation's position in our sky is not coincidental either. Sagittarius lies directly on the ecliptic, the fundamental plane along which planets orbit our sun. 3 Atlas's trajectory aligns within a mere 5 degrees of this plane, an orientation that, for a random interstellar object, carries only a 0.2% probability. However, if one were deliberately targeting a solar system, planning a survey mission or initiating contact, an approach along the ecliptic would be the most logical course. That's precisely where the most significant celestial real estate resides: the rocky inner planets, the gas giants, the asteroid belt, and the Kuiper belt objects. An approach perpendicular to the ecliptic would drastically minimize the time spent within the plane containing these targets. Conversely, an approach along the ecliptic maximizes the potential for interaction. Ancient astrologers associated Sagittarius with the 9th house, the celestial domain governing long journeys, foreign lands, philosophy, and higher learning. They could not have foreseen interstellar space or the intricate structure of our galaxy. They could not have predicted that their Archer constellation would ultimately point towards the literal, physical center of our cosmic home. Yet, here we stand, receiving visitors from precisely that direction. Visitors who present humanity with its most profound philosophical quandaries to date. The synchronicity is almost uncanny. December 19th carries its own symbolic weight. Occurring just 6 days before Christmas, during the deepest part of the year for Northern Hemisphere civilizations, a time when ancient peoples ignited fires against the encroaching cold and recounted tales of stars, gods, and cyclical renewal. The winter solstice, the moment when the sun reaches its lowest point before beginning its northward return, arrives a mere 2 days after the projected arrival date. Nearly every major culture in the Northern Hemisphere has developed some form of light festival around this period. Hanukkah, Christmas, Yule, Dongji, Dies Natalis Solis Invicti, all celebrating the return of light, the persistence of hope, the promise that darkness is not an eternal state. Now we await a different kind of illumination, a harbinger of either promise or threat, arriving precisely within this charged symbolic interval. Some religious scholars are already drawing parallels, speaking of celestial signs, portents of profound transformation or imminent judgment. Others dismiss these interpretations as mere coincidence, emphasizing that December 19th is simply another day, and that our cultural associations hold no sway over orbital mechanics or extraterrestrial intentions. However, symbols undeniably resonate with humans, even if they hold no physical significance. The very fact that this potential first contact is unfolding during a season traditionally associated with gift-giving, with visitors bearing presents and auspicious tidings, profoundly colors our perception of the event. Avi Loeb's evocative phrase, referring to the probes as potential Christmas gifts to humanity, was far more than mere rhetorical flourish. It tapped into deeply ingrained cultural narratives concerning strangers bearing valuable offerings, about surprising arrivals that irrevocably alter the course of history. The Pleiades add yet another layer to this intricate tapestry. When 3 Atlas was first detected in early July, the Moon executed a rare occultation, passing directly in front of the Pleiades star cluster, an event that occurs only once every few years. The Pleiades, often called the Seven Sisters, comprise 7 brilliant stars within Taurus, the Bull, another constellation of the zodiac. Greek mythology links them to Atlas, the Titan condemned to bear the heavens upon his shoulders, whose 7 daughters were transformed into this celestial cluster, as a divine punishment for their father's defiance of Zeus. The resonance of this name is not lost on anyone involved. 3 Atlas, discovered during a lunar occultation of the Pleiades, releasing 7 probes towards targets in the inner solar system. 7 sisters, 7 probes, 7 entities carrying unknown purposes towards our small world. These patterns, undeniably, might signify nothing at all. The universe is vast, infinitely complex, and replete with coincidences. We are, by our very nature, pattern-seeking creatures, evolved to discern signals amidst the cacophony of noise, for the simple reason that missing a genuine pattern could mean extinction. Conversely, perceiving false patterns merely represents a diversion of our cognitive resources. Our ancestors, who perceived potential predators in every fleeting shadow, survived far more effectively than those who waited for absolute certainty. Thus, we find meaning everywhere, weaving connections between phenomena that may be entirely independent. This, in essence, is a feature, not a bug, of human cognition. But what if, on occasion, these patterns are indeed real? What if some coincidences are not mere happenstance? What if a civilization capable of dispatching probes across light years is also capable of selecting arrival times that resonate with the target civilization's cultural frameworks, capable of imbuing their actions with symbolic weight to maximize psychological impact? If we possessed such capabilities, we would undoubtedly employ them. When the Voyager Golden Record was being conceptualized, immense care was invested in selecting images and sounds that would not only convey information, but also imbue it with meaning, presenting humanity in ways we ourselves deemed significant and representative. Why would we assume aliens possess less thoughtful intentions? The heart of our galaxy, even without the elusive 3i Atlas, remains a profound mystery. We know a black hole resides there, its mass calculable by observing the stellar dance around it, yet its presence remains unseen directly. Astonishingly, young stars flourish near this galactic core, defying the intense radiation that should stifle star birth. Their very existence there is an unanswered question. Furthermore, this region bombards us with gamma rays, X-ray flares, and radio bursts, some exhibiting patterns that defy our current understanding. It's a cosmic laboratory, a realm of extreme physics where our established models falter, hinting at phenomena yet to be uncovered. Imagine a civilization yearning to explore the galaxy, to grasp the intricate processes of star and planet formation across diverse cosmic settings. The galactic center, with its dense stellar population, abundance of heavy elements, and ceaseless activity, would be an ideal launchpad. From this concentrated area, they could survey thousands of star systems and dispatch probes to the quieter, more sparsely populated reaches of the galaxy. Consider our own solar neighborhood, where stars endure billions of years of solitude, and where, perhaps, unusual phenomena like technological civilizations might occasionally bloom. This line of reasoning, of course, is layered speculation, a blend of cosmic wonder and astronomical observation, where pattern recognition runs unchecked by definitive proof. Yet, it's precisely this kind of imaginative inquiry that can spark profound insights, prompting questions that rigid adherence to proof might overlook. Scientific progress thrives on bold hypotheses, rigorously tested against careful data. Currently, we possess an abundance of hypotheses, but a scarcity of concrete data. However, December the 19th promises to dramatically shift this balance, one way or another. The probe swarm, now identified by informal names rather than official designations from the International Astronomical Union. Those will require months to finalize through proper bureaucratic channels. These working labels are essential for astronomers and military analysts to track and distinguish them amidst a growing deluge of observational data. Probe 1 through Probe 7, uninspired yet functional labels, each representing a 30-meter enigma hurtling through space with purposes we can only speculate upon. Probe 1, the largest and most luminous, is the one truly capturing everyone's attention. Its trajectory has been meticulously refined each night, and these adjustments consistently confirm a single, unsettling prediction. Its closest approach on December the 19th at 3:15 Universal Time, a mere 8.7 million kilometers away, with an encounter velocity of approximately 45 kilometers per second. While this velocity is modest for an interstellar object, it is staggeringly fast by human standards. 45 kilometers per second is 9 times faster than the most ambitious spacecraft we have ever launched, swift enough to traverse the distance between Earth and the Moon in under 3 hours. But here's what sets Probe 1 apart. Its deceleration is ongoing. The object continues to slow, shedding velocity at a measurable rate. This indicates that its engines, whatever form they may take, are still active, consuming fuel or reaction mass, generating thrust days after its initial separation at perihelion. Natural celestial bodies do not behave this way. Once detached from a parent body, once propelled by its ejection mechanism, an object simply coasts, governed by the conservation of momentum and Newton's first law. An object in motion remains in motion unless acted upon by an external force. Probe 1, however, is demonstrably being acted upon by an external force, its own propulsion system. Furthermore, the deceleration pattern appears controlled, not the steady burn of a chemical rocket expending its fuel, but a variable thrust, waxing and waning in a manner suggesting active guidance. Someone, or something, is steering, making course corrections, precisely tuning the trajectory to arrive at a specific point in space and time. Dr. Margaret Ann Kuo at NASA's Jet Propulsion Laboratory has been employing increasingly sophisticated algorithms to model Probe 1's trajectory. Her latest projections reveal a scenario that has transformed her initial skepticism into profound concern. If Probe 1 maintains its current deceleration profile, slowing at the observed rate for another 3 weeks, it will match Earth's orbital velocity, not merely passing by, not hurtling past us at 45 kilometers per second, but pacing us. It will achieve what orbital mechanics terms a rendezvous trajectory, where two celestial bodies moving through space arrive at the same point with comparable velocities, facilitating extended interaction, docking, or even capture. This capability fundamentally alters the situation. A probe capable of rendezvousing with Earth could potentially enter orbit. It could establish a fixed position, observing for extended periods, perhaps months or even years, meticulously studying our planet, our cities, our communications, our activities, compiling detailed reports on this unexpected technological species it has encountered. Or it could pursue other objectives. It might deploy additional payloads, establish a permanent presence, or simply wait, a silent, alien observer, awaiting instructions from its origin on how to proceed with its meticulously designed mission. Probe 2 embarks on an entirely different path. Its closest approach is scheduled for December the 20th at 1740 Universal Time, at a distance of 9.2 million kilometers. However, its velocity curve is peculiar. Instead of the steady deceleration seen in Probe 1, Probe 2 maintains a nearly constant velocity, with only minor course corrections. It is projected to speed past Earth at 48 kilometers per second, close enough for exceptional remote sensing but too swift for capture or rendezvous. Its projected trajectory after encountering Earth directs it back towards the outer solar system, suggesting it might function as a reconnaissance probe rather than a mission intended for landing. Its purpose appears to be observation and reporting, not lingering. The photometry of Probe 2 exhibits distinct characteristics compared to Probe 1. Its brightness fluctuations are more erratic, less geometrically consistent. Some analysts interpret this as evidence of surface features, possibly instruments or antennas extending from its primary structure. When designing a probe for close-range flyby observations, optimal sensor coverage would be paramount, with cameras, spectrometers, and radar systems oriented in multiple directions to gather data during the brief encounter window. Probe 2 might well be engineered for this specific mission profile, adorned with instruments that contribute to a less symmetrical appearance than its counterparts. Probe 3 remains an enigma. Its orbit has proven particularly challenging to map, complicated by apparent trajectory adjustments that deviate from simple ballistic paths. Certain observations suggest it is executing minor course corrections every few days, adjustments far too precise to be attributed to outgassing effects. The most recent orbital solutions place its closest approach on December the 18th, a day earlier than the other probes, at 10.1 million kilometers. However, these solutions are accompanied by substantial error margins, uncertainties that will not be resolved until radar tracking becomes feasible in mid-November. What makes Probe 3 particularly intriguing is its rotational state. Unlike Probes 1 and 2, which maintain stable spins with predictable 16-hour periods, Probe 3 appears to be tumbling erratically, its brightness variations chaotic, indicating uncontrolled rotation around multiple axes. This could signify damage sustained during its separation from the mothership. Alternatively, it might be an intentional design feature, a probe engineered to sample the surrounding space environment from constantly shifting orientations, thereby maximizing data collection by exposing different sensor arrays to various celestial perspectives. Then there are the Venus probes, 4 and 5. Their trajectories diverge dramatically from those directed toward Earth, bending inward towards the Sun rather than outward. Venus reaches its inferior conjunction, its closest approach to Earth, in January. And it is at this time that these probes are expected to arrive. Venus is a hellish world, an 800-degree inferno with crushing atmospheric pressure and clouds of sulfuric acid. Nothing humanity has sent there has survived for more than a couple of hours before succumbing to the extreme heat and corrosive environment. Yet, Venus is also a crucial laboratory for studying runaway greenhouse effects, atmospheric superrotation, and the very limits of planetary habitability. If one is surveying a solar system, striving to understand the full spectrum of terrestrial planet conditions, Venus is an indispensable data point. The Venus probes are smaller than their Earth-bound counterparts, or at least they appear dimmer, suggesting either a reduced size or different surface properties. They are not decelerating with the same intensity, which is understandable given Venus's thick atmosphere, which could be utilized for aerobraking. If these probes are designed to enter the Venusian atmosphere, they would require less propulsion fuel, as they could descend and allow atmospheric friction to perform the deceleration, though they would necessitate extraordinary thermal protection to withstand even brief exposure to such conditions. Probe 6 is designated for Mars. Its trajectory is the most gradual, the most unhurried of the 7, a gently curving path that will bring it into proximity with the red planet in March of 2026, 4 months from now. Mars is currently positioned on the opposite side of the Sun from Earth, geometrically separated, but still accessible to a probe possessing patience and ample fuel reserves. The trajectory for Mars demands less delta V, or change in velocity, than the Earth-bound trajectories because Mars is farther from the Sun, situated deeper within the Sun's gravitational well, and orbits at a slower pace. In fact, it represents the most energy-efficient target among the inner planets for an object approaching from interstellar space. However, Mars possesses something Earth lacks: unambiguous evidence of human activity. Rovers and landers, orbital satellites, and habitats that might one day support permanent settlements. If one is studying a local technological species, Mars provides insights into expansion capabilities, our reach beyond our home world, and whether humanity is confined to a single planet or is indeed spreading outward. Probe 6 will have the opportunity to observe our off-world infrastructure up close, assuming it achieves sufficient proximity and our Martian assets remain functional upon its arrival. The 7th probe, designated the Outlier, is heading away from the inner solar system back towards the gas giants, following a trajectory that will take it past Jupiter in June of 2026, approximately 8 months from now. Jupiter, the monarch of planets, boasting 300 times Earth's mass, is essentially a scaled-down star that narrowly missed igniting. Its magnetic field is colossal, its radiation belts lethal, and its moons a diverse collection of alien worlds, from the volcanically active Io to the ice-covered Europa. and the immense Ganymede with its subterranean ocean. Jupiter represents a planetary environment fundamentally distinct from the rocky inner worlds, and its survey completes the dataset. Probe 7 also ranks as the brightest after Probe 1, indicating a comparable size or superior reflectivity. Its trajectory aligns more closely with 3I Atlas than any of the other 6, as if it is escorting the mothership, maintaining formation as both journey outward. Some analysts hypothesize that this could be the communications relay, the probe tasked with gathering data from its 6 siblings and transmitting consolidated reports back to 3I Atlas, or even further. If one intends to dispatch probes to 7 distinct targets, a mechanism for collecting their findings is essential. Probe 7 could fulfill this role, acting as a central hub, the mission coordinator ensuring all collected data reaches its destination. The separation event itself remains shrouded in mystery. Juice observed the aftermath. 7 objects already distinct and dispersing, but did not capture the precise moment of release. What forces were involved? Did 3I Atlas fragment violently, breaking apart under thermal stress or tidal forces? This explanation is invalidated by the fact that the mothership remains intact, continuing on its original trajectory with no apparent mass loss beyond normal cometary outgassing. Did it eject the probes mechanically, employing some form of launching system? Spring-loaded mechanisms, compressed gas ejection, electromagnetic catapults? These are technologies we comprehend, scaled to alien engineering standards, but conceptually familiar. Or was the process more gentle? Did the probes detach and drift away under minimal impulse, subsequently activating their own engines once clear of the mothership? This would minimize mechanical stress and allow for a more controlled separation. However, it necessitates the probes carrying their own propulsion systems from the outset, adding mass and complexity. Regardless of the method, the separation was a deliberate act. 7 objects do not spontaneously arrange themselves into trajectories targeting 7 distinct solar system bodies by mere chance. The precision of targeting alone demands navigational data, an understanding of planetary positions months in the future, calculations accounting for gravitational forces and orbital motion, and intricate interception geometry. There exists another possibility, one that fewer scientists are eager to discuss publicly. What if the probes were always separate entities? What if 3I Atlas is not a mothership but a convoy? 7 independent spacecraft flying in formation across interstellar space, cloaked or camouflaged in such a way as to appear as a single object until perihelion, at which point they drop the pretense and diverge towards their assigned targets. This scenario implies even more sophisticated technology, active stealth systems, and meticulously coordinated flight controls and deception planning. It also suggests intentions that warrant concealment, reasons to mask their true nature until the decisive moment of commitment. The tracking data will improve dramatically once radar systems become operational. Radio waves can measure distances and velocities with a precision unattainable by optical observations. Radar can also detect surface properties, including roughness and composition, and potentially even large-scale structures if the return signals are sufficiently strong. The Arecibo Observatory would have been ideal for this purpose, its massive dish in Puerto Rico tragically collapsing in 2020, a loss still keenly felt by the astronomical community. However, other facilities remain operational. Goldstone in California, Greenbank in West Virginia, and the planetary radar systems at NASA's Deep Space Network all will be directed towards the probes once they enter effective range. Military installations are also tracking them, utilizing systems not primarily designed for scientific observation, yet perfectly capable of it. Early warning radar networks, ballistic missile defense sensors, and installations whose very existence is classified but whose capabilities are widely acknowledged by those who pay close attention. These systems can track objects far smaller and faster than anything resolvable by civilian telescopes. They are continuously monitoring the probes, feeding data into threat assessment models, calculating impact probabilities, even though an impact is exceedingly unlikely given their projected trajectories. unless the trajectories change again. That fear is the driving force behind the redundant tracking and the obsessive monitoring. If the probes could alter course once, they can do so again. If they possess fuel reserves for rendezvous maneuvers, they certainly have fuel reserves for targeting maneuvers. An object capable of matching Earth's orbital velocity could, with sufficient propulsion authority, also dive towards Earth's surface. The mathematics involved are straightforward and unforgiving. Until we ascertain the precise capabilities of these probes, we cannot dismiss scenarios where close observation could escalate into something far more consequential. The Fibonacci transmission's radio silence persisted for precisely 9 days. From perihelion on October the 29th until November the 7th, there was complete silence. The Allen Telescope Array in California, the Parkes Observatory in Australia, the Effelsberg dish in Germany. Every major radio telescope capable of monitoring the hydrogen line frequency was actively listening, diligently recording endless hours of cosmic noise, but nothing resembling a structured signal. Natural radio emissions from Jupiter, solar radio bursts, the pervasive hiss of our own galaxy's background radiation. All the usual celestial suspects were present, but no Fibonacci sequences, no discernible patterns, and no repetition of those captivating pulses detected by the Parker Solar Probe during its perihelion passage. Then, on November the 7th, at 2:37 Universal Time, the Very Large Array in New Mexico detected something. Not from 3i Atlas itself, which remained radio quiet, but from one of the probes, Probe 1 specifically, the Earth-bound object that has been continuously decelerating. A burst of narrowband emission centered at 1.420 GHz, the hydrogen line, lasted 3.14 seconds, followed by 5.08 seconds of silence, then another burst of 8.04 seconds, succeeded by 13.10 seconds of silence. This pattern continued for 26 minutes. Burst, silence, burst, silence. Each transmission was progressively longer than the previous, adding the durations of the two preceding transmissions, 3, 5, 8, 13, 21, 34, 55, 89, 144. The Fibonacci sequence, unmistakable and deliberate, was present once more. But this time, there was more. Within each burst, within those precisely timed transmissions, lay structure, modulation, information encoded in variations of signal strength and frequency. Dr. Rachel Kim at the SETI Institute, who has been leading the analysis of these transmissions, reports preliminary findings that are both frustrating and tantalizing. The modulation is clearly not random. It exhibits regularities, patterns within patterns that strongly suggest intentional encoding rather than natural variation. However, deciphering the code, extracting meaning from these intricate patterns, has proven exceptionally challenging. We are attempting to decode a message from a civilization about which we know absolutely nothing. We are employing mathematical relationships that we presume to be universal, but which might be implemented in ways we cannot yet anticipate. Kim's team has explored every avenue, treating the modulation as amplitude encoding, frequency encoding, and phase encoding. They have searched for prime numbers, mathematical constants, geometric ratios, and tested whether the signal might represent images, one-dimensional data that could be assembled into two-dimensional pictures. Nothing yielded a conclusive result, or rather, everything produced partial successes, generating outputs that appeared almost meaningful but never quite resolved into clear, unambiguous information. It is akin to tuning a radio to a station that is slightly off frequency. You catch fragments, hints of structure, but never the complete clarity that confirms understanding. This frustration is exacerbated by the fact that this situation aligns precisely with the predictions of first contact theorists. Communication between species that evolved independently, developing mathematics, logic, and information encoding in potentially divergent ways, was never anticipated to be straightforward. The hydrogen line frequency serves as a universal common ground, a wavelength that any technological civilization would readily recognize. However, once a shared channel for transmission is established, conveying complex information necessitates shared assumptions about data structure, which may not be present. There exists a philosophical argument positing that mathematics is universal, that 1 + 1 invariably equals 2 throughout the cosmos, and that geometric relationships and physical constants provide objective common ground. But the practical implementation matters profoundly. We utilize base 10 because we possess 10 fingers. A species with different anatomy might adopt base 8, base 12, or base 16. We represent numbers as sequential symbols arranged from left to right. They might employ an entirely different system. The underlying mathematical principles could be identical, while the notation remains mutually incomprehensible. Kim's latest approach involves interpreting the transmissions as a tutorial, an attempt by Probe 1 to instruct us in its encoding scheme. This is precisely how we would endeavor to communicate with a newly discovered intelligence. Begin with simplicity, establish basic correspondences, and gradually progress to more complex concepts. The Fibonacci sequence itself might constitute Lesson 1, demonstrating our shared understanding of mathematical patterns. Subsequent transmissions could introduce additional concepts, thereby creating a shared vocabulary understood by both parties. However, this process requires time, patience, and ongoing dialogue. If Probe 1 only transmits every few days, sending tiny bits of new information each time, it could take us weeks, maybe even months, to build enough shared knowledge to truly understand each other. But we don't have that kind of time. We have just 42 days until arrival. 42 days to go from knowing basic math to understanding complex intentions and giving clear instructions. Unless we reply, unless we send back a confirmation that we've received their messages and can demonstrate our own grasp of mathematics, the debate rages. Scientists and government advisors are deeply divided, seeing the situation through vastly different lenses of risk and opportunity. One side argues for an immediate response. They believe every day we remain silent is a wasted opportunity to initiate contact and begin the vital process of mutual understanding. If Probe 1 is reaching out, our silence could easily be mistaken for hostility or a simple lack of comprehension. We might be letting slip our only chance to connect with an extraterrestrial intelligence simply because we're too hesitant, too fearful of what might happen. And honestly, what could we possibly say that would make things worse? If they intended harm, they wouldn't need our permission. If they are peaceful, ignoring their overture seems entirely counterproductive. The other side, however, urges extreme caution. They emphasize that we know virtually nothing about these visitors, their intentions, their capabilities, or the civilization that dispatched them. Responding immediately would confirm our existence and our level of technological advancement, leaving no doubt that Earth is home to intelligent life. It would also reveal details about our mathematics, our communication methods, and our overall progress. This information, they argue, could be precisely what the probes are seeking, and offering it freely without understanding their motives could be a catastrophically foolish mistake. History is replete with cautionary tales of civilizations that revealed themselves to more powerful neighbors, and first contact doesn't always bode well for the less advanced party. For now, officially, humanity is listening but not transmitting. The established protocols from the International Academy of Astronautics for responding to extraterrestrial signals endorse precisely this measured approach. Confirm detection, analyze the content, consult with international bodies, and only then consider response options, with input from all of humanity, not just individual nations or institutions. These protocols, however, were conceived for signals originating from distant star systems, civilizations light years away, where response times would be measured in decades. No one anticipated needing them for objects approaching Earth on a timescale of mere weeks. Unofficially, though, some groups are far less patient. Amateur radio astronomers, equipped with powerful transmitters, have been directing their signals at Probe 1, sending their own messages. These include mathematical sequences, lists of prime numbers, images of Earth and human faces, and even recordings of music and natural sounds. It's akin to throwing spaghetti at the wall to see what sticks, a chaotic, uncoordinated effort, likely adding noise to any genuine attempts at communication. Yet, it's happening anyway, because trying to dissuade amateur astronomers from transmitting is about as effective as telling the tide not to rise. China, meanwhile, is pursuing its own distinct strategy. Their asteroid sample return mission, Tianwen-2, launched in May, has been quietly retargeted. Originally, its objective was to collect material from the near-Earth asteroid 2016 HO3 and bring it back to Earth. But thanks to sufficient propulsion reserves and meticulous trajectory planning, the spacecraft could instead rendezvous with one of the 3 Atlas probes. Not Probe 1, as it's too fast and too distant, but potentially Probe 3 or 6, depending on how orbital mechanics align. Tianwen-2 is equipped with instruments for compositional analysis, cameras for detailed imaging, and even a sampling arm capable of collecting material from a probe's surface, provided it can get close enough. The potential scientific rewards are immense: direct observation, chemical analysis, perhaps even samples of extraterrestrial technology. However, the risks are equally monumental. What if a probe perceives a close approach as an act of aggression? What if it possesses defensive systems we cannot foresee? Could China's unilateral action provoke responses from the probes that affect everyone, not just the nation undertaking the approach? NASA is aware of China's intentions, of course. Satellites designed to track asteroid missions can readily monitor course changes and trajectory projections. There have been stern diplomatic exchanges, threats of sanctions, and accusations of reckless endangerment of humanity for nationalistic gain. But China remains resolute. They argue, with considerable justification, that gathering direct data on the probes is crucial, regardless of who conducts the mission. It's far better, they contend, to understand what we're dealing with than to remain ignorant until December 19th. And if, in the process, they happen to secure exclusive access to revolutionary alien technology, well, that would simply be a fortunate byproduct of their bold scientific endeavor. The signals persist, arriving every 3 to 4 days. Probe 1 transmits again, on the same frequency, with the same Fibonacci timing, but with subtle variations in its modulation patterns each time. The data is being meticulously archived, with multiple institutions maintaining independent copies to safeguard against loss from individual system failures. Analysts are painstakingly comparing these transmissions, searching for evolutionary patterns, trying to ascertain whether the probe is repeating information or building upon previous messages. A particularly intriguing detail emerged from comparing the transmissions of November 7th and November 11th. The signal's strength fluctuates in a pattern that defies any known physical process. It doesn't follow the inverse square law, the natural decrease in signal intensity with distance. It's not influenced by rotation or changes in orientation. Instead, these variations appear deliberate, as if the probe is actively adjusting its transmission power to maintain a consistent reception strength on Earth, despite its increasing distance. This suggests an awareness of Earth's location and our receiver's sensitivity. Information the probe shouldn't possess unless it has been observing us for longer than we've been aware of it, or unless it received this data from the 3 Atlas. The mothership had months to study Earth as it approached, months to map our radio emissions, our television broadcasts, and our radar transmissions. All of that data, all those inadvertent signals we broadcast into space, simply by operating our technological civilization, could have been analyzed and compiled into a comprehensive briefing. Probe 1 might already know everything about us that electromagnetic radiation can reveal. All our languages, our communication protocols, our technological capabilities, while we know virtually nothing about it beyond its trajectory and timing. This asymmetry is profoundly unsettling. We are the transparent party, broadcasting every detail about ourselves to anyone with the right receivers and processing power. They, in turn, remain an enigma, revealing only what they choose through carefully controlled transmissions. It's the antithesis of how first contact scenarios typically unfold in fiction, where Earth sends out messages and waits hopefully for a response. This time, they are transmitting, and we are the ones grappling with the decision of how to reply, acutely aware that whatever we say or do might be monitored, analyzed, and fed into decision-making processes we cannot comprehend. The cyanide issue adds another layer of perplexing mystery. Spectroscopic observations of Probe 1 indicate emissions consistent with hydrogen cyanide, that infamous poisonous compound, smelling faintly of bitter almonds, which disrupts cellular respiration. Comets naturally produce cyanide as they break down organic compounds under solar ultraviolet radiation, so its presence isn't inherently suspicious. However, the concentrations detected are extraordinarily high, far exceeding what would be expected from normal cometary chemistry, especially for an object that separated from its parent body weeks ago and should have ceased producing new volatile compounds. Hydrogen cyanide is also noteworthy from a chemical signaling perspective. It's simple enough to produce deliberately. Just carbon, nitrogen, and hydrogen in the correct configuration. It possesses strong spectral signatures easily detectable across interstellar distances. And crucially, it's toxic to life as we know it, potentially serving as a universal warning signal for hazardous conditions. Is Probe 1 attempting to communicate danger, to warn us away, signaling that it carries payloads we wouldn't survive exposure to? Or could the cyanide serve a different purpose, perhaps related to propulsion, or simply a byproduct of its operational power systems? David Serita's hyperdimensional theories have suddenly gained unexpected traction in the context of these transmissions. Serita has long posited that advanced civilizations might communicate not just through electromagnetic radiation, but also by manipulating dimensions. His ideas, once considered fringe and barely respectable within mainstream physics, are now being re-examined. What if the radio transmissions are merely the accessible layer, a component of a multi-dimensional message that our crude three-dimensional instruments can detect? What if there's additional information encoded within space-time curvature, within quantum entanglement patterns, or aspects of reality we know exist but cannot yet effectively measure? It sounds like science fiction, like mysticism cloaked in physics terminology. But the uncomfortable truth is that we lack sufficient knowledge to definitively dismiss these possibilities. Our understanding of physics is incomplete. Our grasp of reality is provisional. We are still striving to reconcile quantum mechanics and general relativity, still searching for theories that unify fundamental forces, explain dark matter, and predict phenomena within black holes. A civilization millions of years our senior might have already solved these profound problems and could be operating on principles we haven't even discovered. Their communications might contain layers we are blind to, crucial information we are missing simply because we are looking in the wrong dimensions. Let's delve into the technology assessment, examining what's realistically achievable versus what we are observing. This is where rigorous engineering principles collide with uncomfortable realities, where theoretical calculations yield numbers that challenge our fundamental assumptions about technological capabilities. Consider heat, for instance. At its closest approach to the Sun, the 3I Atlas absorbed 770 watts of solar radiation per square meter of its surface area. While this is roughly half of what Earth receives and seemingly manageable by our standards, it was applied continuously to an object devoid of an atmosphere for convective cooling and possessing limited thermal mass. Natural comets typically cope with this through ablation, shedding surface material that carries heat away as it evaporates. Ice sublimates, organics decompose, and the resulting gas flow acts as a cooling system. It's a crude but effective mechanism. Yet, the 3I Atlas did not fragment, did not undergo explosive decomposition, and did not dramatically brighten due to runaway outgassing. It passed perihelion remarkably intact, losing an estimated 2 million tons of material, according to Avi's calculations, a mass loss representing less than 0.5% of its total bulk. This ratio, this remarkable ability to maintain structural integrity while shedding minimal mass under intense thermal stress, surpasses anything observed in natural comets. The probes themselves present even greater challenges. Each is estimated to be 35 meters long and perhaps 12 meters in diameter, based on light curve analysis. Their materials are reflective enough to be visible across hundreds of millions of kilometers, yet not so reflective that they would overheat in direct sunlight. The thermal balance for objects operating in space is incredibly delicate. Excessive absorption leads to overheating of electronics, while excessive reflection results in freezing. Spacecraft designers invest enormous effort in optimizing surface coatings, radiator sizes, heat pipe configurations, everything necessary to maintain operational temperatures. These probes are managing these complex thermal loads autonomously, without ground support, and with no ability to request assistance if something malfunctions. They have been effectively handling thermal loads for weeks, from the intense solar exposure at perihelion through their current locations millions of kilometers from the Sun, and they remain functional, continue transmitting, and are actively maneuvering. This implies exceptionally robust engineering, redundant systems, and materials and designs capable of withstanding wide temperature fluctuations without degradation. The propulsion system is the dominant question in every technical discussion. How much fuel is involved? What type of engine is being used? What are its performance characteristics? Let's start with the fundamentals. Probe 1 has decelerated from an astonishing 68 kilometers per second to its current velocity of approximately 47 kilometers per second. This represents a delta V, a change in velocity, of 21 kilometers per second. To provide perspective, the Apollo missions to the Moon required a total delta V of about 11 kilometers per second from Earth's surface to lunar orbit and back. Probe 1 has executed nearly twice the entire velocity budget of the Apollo program in a single, sustained maneuver. The rocket equation is unforgiving. Delta V equals exhaust velocity multiplied by the natural logarithm of the initial mass over the final mass. Rearranging this equation reveals the mass ratio, how much heavier the object must be at the start compared to the end. For conventional chemical rockets with exhaust velocities around 4 kilometers per second, achieving a 21 kilometer per second delta V would necessitate a mass ratio of approximately 200 to 1. This means 200 kilograms of fuel and rocket for every single kilogram of final payload. Such a ratio is utterly unachievable for anything resembling a spacecraft as we understand it. The fuel tanks alone would weigh more than the structure could possibly support. Higher performance engines alter the mathematical equation but do not fundamentally change these constraints. Ion drives, with exhaust velocities ranging from 30 to 50 kilometers per second, offer improved mass ratios, but at the cost of such low thrust that maneuvers would take months or even years to complete. Probe 1's deceleration, occurring over a span of mere weeks, effectively rules out standard ion propulsion. Nuclear thermal rockets could achieve exhaust velocities of 8 to 9 kilometers per second, significantly enhancing the mass ratio, but still requiring fuel fractions around 80% for the observed performance. That's 80% fuel, leaving only 20% for everything else. This might be achievable with extremely optimized engineering, but it pushes the boundaries of what physics permits. Fusion power changes everything. If controlled fusion can be achieved, if reaction mass can be heated to temperatures where nuclei fuse and release energy according to E equals mc squared, exhaust velocities measured in percentages of the speed of light become possible. 1% of the speed of light is 3,000 kilometers per second. With that level of performance, achieving a 21 kilometer per second delta VO becomes almost trivial. The mass ratio drops to just slightly above 1 to 1, meaning the craft is predominantly payload with only a small fuel fraction required for maneuvers. However, fusion is exceptionally challenging. We've been attempting to achieve net energy gain from fusion for 70 years, investing billions and constructing increasingly large experimental reactors. And only now are we approaching conditions where energy output equals energy input. Sustained, controlled fusion suitable for spacecraft propulsion remains purely theoretical. We have concepts, designs on paper, and computer simulations that suggest its feasibility, but we have yet to build such a system. We don't know how to construct one with our current technology and materials. If the probes are utilizing fusion, They represent technology that is, by conservative estimates, centuries ahead of our own. If they are employing something else entirely, something beyond fusion, the technological gap widens even further. Antimatter propulsion offers exhaust velocities approaching the speed of light, but requires the containment and control of the most explosive substance imaginable. Then there are concepts like black hole drives or vacuum energy extraction or reactionless drives that push against space-time itself. All of these exist within theoretical physics papers, but nowhere else. They represent the kind of technology that demands not just engineering advancements, but fundamental breakthroughs in our understanding of reality itself. Finally, we must consider the navigation challenge. Probe 1 is targeting a region the size of Earth's Hill sphere, the domain where our gravity exerts dominant influence, starting from a point hundreds of millions of kilometers away, all while traveling at velocities that would traverse that entire distance in mere weeks. The required precision is staggering. A deviation of just 1/1,000,000th of a degree in the initial trajectory would result in an error of thousands of kilometers upon arrival. Natural celestial bodies do not hit targets with such accuracy. They follow ballistic paths dictated by gravity and initial conditions, landing wherever physics directs them. Guided objects, spacecraft equipped with sensors, computers, and control authority, can achieve precise targeting, but this necessitates real-time navigation, continuous positional updates, and trajectory corrections applied at precisely the right moments with exactly the correct magnitudes. It requires knowing one's current position, the target's future position at the time of arrival, and having the capability to connect these points via a path executable by the propulsion system. The probes have been accomplishing this for weeks without any discernible communication with the 3i Atlas or with each other. They are navigating autonomously, using onboard sensors to track stars, planets, or perhaps even radio signals from Earth, processing this data to determine their positions and velocities, calculating necessary corrections, and executing engine burns without any external guidance. The computational capability alone is remarkable. Modern spacecraft navigation typically relies on ground support, mission-controlled teams with supercomputers, and extensive planning that can take weeks for major maneuvers. These probes are performing these complex tasks themselves in real time, with a level of reliability that has shown no obvious errors. The phenomenon of the anti-tail continues to perplex researchers. During July and August, the 3i Atlas exhibited a peculiar sunward jet, with gas and dust streaming towards the sun rather than away from it, as is typical for cometary tails. Natural processes can indeed produce anti-tails under specific geometric viewing conditions, where perspective effects make tail material appear sunward when it is actually oriented perpendicular to our line of sight. However, detailed analysis conclusively showed this was not a matter of geometry. The material was demonstrably moving towards the sun against the forces of solar wind and radiation pressure, propelled by forces that demanded an explanation. One plausible hypothesis involves rotation-induced jets. If a comet is spinning and possesses active vents in specific locations, outgassing can generate thrust in non-radial directions, including sunward under certain orientation combinations. However, this explanation requires highly specific rotation rates and vent configurations, conditions that seem rather contrived when attempting to account for the 3i Atlas's behavior. The alternative, and the one that causes engineers considerable unease, is that the anti-tail was propulsive, a rocket plume with reaction mass expelled in controlled directions to adjust its trajectory. If the 3i Atlas was performing trajectory corrections in July and August, if it was fine-tuning its approach to optimize perihelion conditions or probe deployment geometry, then active propulsion would perfectly explain the anti-tail. It would also account for the disappearance of the anti-tail in September, once these maneuvers were completed. Material science enters the discussion when considering the structural loads involved. 35-meter objects maneuvering under significant gravitational forces experience immense stress. The accelerations involved are far from gentle. When velocity is changed by kilometers per second over time spans measured in weeks, average accelerations might appear modest, but peak accelerations during engine burns could be substantial. The structure must withstand these forces while maintaining precise geometric stability for navigation and communication. Human spacecraft are, by comparison, quite fragile. The International Space Station cannot withstand accelerations exceeding a few thousandths of a gravity without risking structural damage. Interplanetary probes are more robust, designed for the rigors of deep space, but they are also carefully balanced and optimized for specific mission profiles with predictable loads. The 3 Atlas probes are navigating an environment we only partially comprehend, executing maneuvers we hadn't anticipated, and enduring stresses we can only estimate. Their structural integrity must be either extraordinarily robust or remarkably over-engineered, or perhaps a combination of both. Power generation presents another enigma. Every action these probes undertake demands energy. Propulsion, communication, computation, thermal regulation. All of it requires watts, kilowatts, or potentially even megawatts, depending on the systems engaged. So, where does this power originate? Solar panels function, but their efficiency wanes with distance from the Sun. At Earth's orbital distance, a square meter of panel area yields approximately 1 kilowatt. Probe 1, assuming a roughly cylindrical form, possesses about 400 square meters of surface area. Even if this entire surface were covered with perfectly efficient solar panels, it would generate only 400 kilowatts. Sufficient for demanding operations, but not limitless capacity. As probes venture farther from the Sun, available power diminishes with the square of the distance. Near Jupiter, solar panels produce a mere 4% of their output at Earth. The outer reaches of the solar system necessitate alternative power sources. Radioisotope thermoelectric generators convert heat from radioactive decay into electricity, but they are heavy and inefficient. Nuclear reactors can produce megawatts but require complex cooling systems, shielding, and intricate engineering. Fusion reactors, if they can be built, offer both power and propulsion in a single package. The probe's power systems must sustain weeks of active operations without any discernible degradation. No dimming of signals, no reduction in maneuver frequency, no activation of energy conservation modes. This suggests either immense energy reserves were packed at launch, or they are continuously generating power through systems that show no noticeable decline over their operational lifetimes. Both scenarios point to technology far beyond our present capabilities. Radiation hardening is far more critical than most people realize. Space is a brutal environment, saturated with particles and electromagnetic radiation that can annihilate electronics. Cosmic rays can flip bits in computer memory, and the accumulated radiation dose degrades semiconductor junctions. Solar storms have the potential to permanently damage or destroy unprotected systems. Human spacecraft mitigate these risks with shielding and redundancy, multiple backup systems designed to prevent single failures from cascading into a mission-ending event. These probes, however, have been exposed to interstellar radiation for potentially billions of years, followed by solar radiation during their approach, and then the intense environment at perihelion where particle fluxes and the electromagnetic fields reach their peak. Yet they persist. Their electronics, whatever form they take, have withstood exposure that would fry every spacecraft humanity has ever constructed. This implies either exceptional shielding, exotic materials that resist radiation degradation, or self-repair mechanisms that mend damage as it occurs. Autonomous operation across interstellar distances and timescales demands a level of reliability we have never achieved. Our longest-serving spacecraft, Voyager 1 and 2, have operated for nearly 50 years, but not without significant component failures and mode shifts. Ground controllers have diligently worked around failing systems, uploaded patches, and switched to backup instruments. These probes lack that luxury. Whatever materials they are composed of, however they are engineered, they must function without maintenance for durations potentially measured in millions of years, traversing environments ranging from the near absolute zero of interstellar space to the searing heat of perihelion passage. Such reliability necessitates engineering philosophies we are only beginning to grasp. Redundancy, certainly, multiple backups for critical systems, but also robustness, designs that can tolerate component failures without a catastrophic loss of function, and perhaps adaptability, systems that can reconfigure themselves in response to damage, that learn, adjust, and continue operating even as subsystems fail. We are researching these concepts for future missions, for spacecraft destined to explore Europa's ocean or land on Titan's methane lakes, but we are far from the level of sophistication these probes demonstrate. Earth's defensive posture. The meetings convene in secure, windowless facilities where phones cease to function. Underground conference rooms, shielded against electromagnetic eavesdropping and accessed through multiple security checkpoints staffed by uncommunicative personnel. This is where military strategists, intelligence analysts, and aerospace engineers gather to deliberate on scenarios that sound like far-fetched science fiction, until one remembers they are planning for actual objects currently approaching Earth at measurable velocities. Space Force, the newest branch of the United States military, has been running simulations since November 3rd. These are not public exercises or theoretical drills, but operational planning utilizing actual tracking data and realistic assumptions about interception windows and engagement parameters. The outcomes are stark. We possess technical options, but none are favorable, and several carry the risk of catastrophic consequences. Option 1 is kinetic interception. The strategy involves launching a missile, something with sufficient delta V to reach probe 1 before it reaches us, and impacting it with the target at high velocity. We have precedent for this. The DART mission in 2022 successfully altered the orbit of asteroid Dimorphos by colliding a spacecraft with it at 6 kilometers per second. The impact measurably changed the asteroid's trajectory, validating the concept for planetary defense against natural threats. However, Probe 1 is not a natural hazard, nor is it as accommodating as an asteroid. The primary challenge is the immense closing velocity. Probe 1 is currently approaching at 47 kilometers per second and continues to decelerate. Any interceptor launched from Earth would add its own velocity to this equation. The total impact velocity could surpass 70 kilometers per second, depending on the trajectory geometry. At such speeds, a 1-ton interceptor possesses kinetic energy equivalent to approximately 500 tons of TNT, enough to damage or destroy a 30-meter object, provided a direct hit is achieved. Targeting presents the second significant hurdle. Probe 1 is actively maneuvering, executing trajectory corrections that suggest the presence of active guidance and threat awareness. A rudimentary projectile, following a predictable ballistic path, would be easily evaded by a maneuvering target, assuming it possesses sensors capable of detecting the incoming threat. And there is every reason to believe it does. Any technology capable of traversing interstellar space and executing precision navigation likely includes basic threat detection capabilities. Equipping the interceptor with its own guidance and terminal homing systems improves the odds, but doesn't resolve the fundamental issue. You are attempting to strike a 30-meter target from millions of kilometers away, while both you and the target are moving at astonishing velocities. The interceptor would require its own propulsion capability, sufficient delta V to make course corrections during its final approach. It would need sophisticated sensors, likely radar, LiDAR, or optical tracking, capable of acquiring and tracking the target through the terminal phase of engagement. Furthermore, it would need a computer fast enough to process sensor data and command trajectory adjustments within mere seconds. At 70 kilometers per second, there is no room for error. We could conceivably construct such a system, perhaps through a crash program with an unlimited budget, relaxed safety protocols, and a considerable amount of luck. We might succeed in designing, building, and launching a viable interceptor before December 19th. But then arises the most unsettling question. What if it succeeds? What if we manage to destroy Probe 1, reducing it to fragments and debris scattered across millions of kilometers of space? In doing so, we would have effectively signaled to whoever sent it that humanity is violent, paranoid, and prone to preemptive action. We would have destroyed potential evidence, eliminated any possibility of peaceful contact or scientific study, and acted out of fear of hypothetical threats rather than any demonstrated act of hostility. Option 2 involves nuclear engagement. If kinetic energy proves insufficient, if the probes are too resilient or too evasive for projectile impacts, the escalation would turn to nuclear weapons. Not detonations on the surface, as no one proposes nuclear explosions in the atmosphere or on land, but in space, where treaties theoretically prohibit such actions. Survival might well supersede diplomatic niceties. Nuclear weapons in space behave differently than in atmosphere. There is no colossal fireball, no propagating blast wave, only intense radiation, an electromagnetic pulse, and, if proximity is sufficient, some debris from the weapon's casing vaporized by the explosion. The radiation itself is the weapon. X-rays, neutrons, and gamma rays flooding outward at the speed of light. Impacting a target with such a flux would superheat its surface, potentially vaporize components, and certainly disrupt or destroy any electronics not exceptionally well shielded. The United States possesses intercontinental ballistic missiles, originally designed to deliver nuclear warheads to targets on Earth. Some of these could be repurposed for space intercepts. Launched on trajectories that intersect Probe 1's path, detonated at their closest approach, they could maximize the radiation dose delivered to the target. This is a crude but potentially effective method if the objective is destruction rather than deflection. However, nuclear engagement in space carries consequences extending beyond the immediate target. The electromagnetic pulse generated by a nuclear detonation propagates through Earth's magnetic field, potentially damaging satellites and power grids, depending on the detonation altitude and yield. The effects could range from localized disruption to hemisphere-wide infrastructure damage. In essence, we would be defending against a hypothetical alien threat by actively causing harm to our own systems. And again, what message does this convey? Deploying nuclear weapons against visitors we do not understand, destroying them without communication or warning, would paint humanity as barbaric and terrified. If other probes, other missions, or other civilizations are observing our conduct during this first contact scenario, a nuclear response would be indelibly etched in their memory. First impressions hold immense weight, even on cosmic scales. Option 3 is less violent, but potentially more provocative. Active denial. This strategy employs non-kinetic systems to interfere with probe operations without necessarily destroying them. High-power lasers could be used to blind sensors, disrupt communications, or even inflict damage on surface components if the beam can be maintained in focus for a sufficient duration. Directed energy weapons do exist, though their capabilities are classified, and their effectiveness against hardened space targets remains uncertain. The advantage of this approach lies in its gradual nature. One could begin with low power, observe the probe's reaction, and systematically escalate, measuring responses and backing off if complications arise. It resembles a chess match more than an all-or-nothing gamble. The disadvantage is that it might prove entirely ineffective if the probes are designed to operate in hostile environments. If they possess countermeasures against directed energy attacks, our attempts could be rendered completely futile while simultaneously being highly irritating to whoever is monitoring their progress. Furthermore, there is the ethical dimension. We would be actively interfering with scientific instruments, potentially compromising observations and data collection. This could very well be the primary objective of the mission. Imagine if aliens had targeted the Hubble telescope with lasers while it observed distant galaxies, or disrupted Voyager during its encounters with Jupiter. We would justifiably be outraged at such a loss of scientific opportunity. Are we prepared to inflict similar damage on others and accept the moral ramifications? Russia has maintained an unnerving silence throughout this unfolding crisis. Their space program has been in decline for years, plagued by budget cuts, corruption, and technological stagnation, reducing them from a superpower to a regional player. Nevertheless, they still possess significant capabilities, including anti-satellite weapons and long-range missiles that could be adapted for space intercepts. The Kremlin has made no public statements regarding Three-Eyed Atlas, or the probes beyond perfunctory acknowledgments that they are monitoring the situation. Intelligence analysts interpret this silence as either a lack of capability or, more disturbingly, a sign of classified preparations they are unwilling to reveal. Russia harbors a historical paranoia regarding threats from above, a cultural memory of invasions and bombardments that can make them potentially quick to act when faced with unknown incoming entities. Should they perceive the probes as an existential risk, they might act unilaterally, bypassing consultation with international partners or consideration of diplomatic repercussions. China's Tianwen-2 mission introduces an unpredictable element into defensive planning. If China successfully achieves rendezvous with one of the probes, if they get close enough for detailed observation or sample collection, will that elicit a response from the probe? Will it alter the tactical landscape for other nations potentially preparing their own intercepts? Coordination would undoubtedly facilitate shared planning and agreed-upon protocols for action. However, coordination hinges on trust and transparency, commodities in critically short supply among nations that view each other as strategic competitors. NATO has activated mutual defense consultation protocols, not yet declaring an Article 5 situation, but acknowledging the necessity for member states to coordinate responses to potential threats. These discussions are complicated by the fact that probes approaching Earth do not recognize national borders. If any incident occurs, an impact, a deployment, or any form of active event, multiple countries will be affected, irrespective of the specific location. Collective security necessitates collective decision-making, but consensus building is a slow process, and December 19th is rapidly approaching. The public is aware of some of this information, disseminated through official statements and press briefings that emphasize preparedness without inciting panic. Most individuals have not altered their daily routines. They continue to go to work, make holiday plans, scroll through social media, and worry about everyday concerns. Cognitive dissonance is a powerful force. When presented with information too vast or strange to process, the brain defaults to normalcy bias, assuming that events will continue as they always have because such large-scale change is literally unimaginable. However, some individuals are preparing, not government planners or military strategists, but ordinary people who have crunched the numbers and determined that December 19th could prove significant. Preppers are stocking supplies not with the expectation that alien probes will disrupt supply chains, but because if something does transpire, if there is disruption, panic, or unforeseen consequences, having food, water, and essential supplies seems prudent. Skeptics deride them, labeling it apocalypse fetishism. But the preppers shrug and point out that preparation is akin to insurance. One hopes never to need it, but one is grateful for its presence if circumstances change. Religious communities are engaging in their own discourse, theological debates exploring the implications of alien life for creation narratives and humanity's place within God's plan. Some denominations are embracing the concept, viewing potential contact as an expansion of divine creation, an opportunity to appreciate and learn from more souls, consciousnesses, or expressions of sacred complexity. Others are troubled, concerned that alien intelligence might undermine biblical uniqueness, suggesting that humanity is not as special or central as Scripture implies. The Vatican, surprisingly progressive on scientific matters for an institution rooted in ancient tradition, has issued measured statements acknowledging that the discovery of extraterrestrial life, including intelligent life, would not contradict Catholic theology. God's creation, the statements note, is vast, and to assume it is confined to a single planet and a single species would be an act of hubris rather than faith. Pope Francis, experienced in navigating complexity and nuance, has approached the three-eyed Atlas situation with cautious optimism, characterizing it as an opportunity for growth and understanding rather than a threat or crisis. Military chaplains are reporting increased attendance at services on bases and installations worldwide. Soldiers, sailors, and airmen facing the possibility of engagement with unknown forces are seeking whatever comfort or meaning their faith traditions provide. Some are praying for peace, for the probes to be benign, and for contact to proceed smoothly. Others are praying for strength and courage, psychologically preparing themselves for actions they might be ordered to take. And some are simply praying for guidance, for the wisdom to navigate unprecedented situations with honor and humanity intact. The defensive posture is immensely taxing. Maintaining a state of high alert, keeping systems ready and personnel trained consumes resources and attention that cannot be sustained indefinitely. If the probes arrive and nothing happens, if they observe and depart without incident, the relief will be profound, but so will the backlash. Politicians will face scrutiny over wasted budgets and unnecessary alarm. Military leaders will defend their caution, arguing that their preparations prevented worst-case scenarios. Even if those scenarios never materialized, society will collectively attempt to forget how narrowly we avoided decisions with irreversible consequences, actions that would have defined humanity's character in the eyes of any intelligences that might be observing. The scientific schism. The divergence did not occur instantaneously. It developed gradually over weeks of observations and debates, fueled by data that resisted conventional explanations, and by the slow realization that this situation would not resolve itself into either clear natural phenomena or obvious artificiality. Instead, it settled into an uncomfortable middle ground where both interpretations remained plausible, depending on which evidence one prioritized. On one side stand the proponents of natural comets, scientists who have dedicated their careers to studying comets and interstellar objects, and who view Three-Eyed Atlas as peculiar, but not impossibly so. Every comet is unique, they contend, shaped by formation conditions we barely understand and evolutionary histories spanning billions of years. Discovering one that behaves anomalously, exhibiting properties outside our limited observational sample size, should not immediately precipitate appeals to alien intelligence. That, they argue, is intellectual laziness, a surrender to the more exciting explanation instead of the arduous work of deciphering natural mechanisms. Dr. Michelle Bannister at the University of Canterbury has been the most articulate advocate for natural explanations. Her research papers on Three-Eyed Atlas emphasize its cometary characteristics: the coma, the tail, and the outgassing, all of which definitively mark it as icy rather than rocky. She points to spectroscopic analysis revealing water, carbon monoxide, and carbon dioxide, precisely what one would expect from a comet formed in the outer regions of another star system and subsequently ejected into interstellar space. The nickel signature, she posits, could be attributed to unusual parent star composition or exotic formation environments yet to be sampled. The absence of evidence, she reminds us, is not evidence of absence. And just because we have not yet witnessed natural nickel fractionation does not render it impossible. The trajectory's alignment with the ecliptic, Bannister continues, is noteworthy but not conclusive. Survey telescopes like Atlas and Pan-STARRS focus on the ecliptic because that is where near-Earth objects reside, and where potential threats are most likely to be detected. Our detection biases are skewed towards finding objects in this plane, because we are actively searching there more intensely than elsewhere. An object approaching from a high inclination might have gone entirely undetected, especially if it was faint and moving rapidly. Therefore, the apparent low probability might actually reflect our detection biases rather than genuine improbability. The survival at perihelion, the fact that Three-Eyed Atlas did not fragment under solar heating, can be explained by its composition. High-density objects, comets with a less porous structure and more refractory materials, can withstand closer solar approaches than their more loosely aggregated counterparts. We've witnessed this phenomenon before with comets that brave the sun's fiery embrace, grazing its surface and emerging unscathed. Comet 3I 2019 Q4, Borisov, or 3I Atlas, never ventured quite that close, maintaining a safe distance well beyond Earth's orbit, so its survival isn't particularly astonishing. As for the fragments, the prevailing theory, championed by Dr. Benko Bannister, suggests natural disintegration. Comets, you see, can fracture, sometimes quite dramatically. Recall comet Shoemaker-Levy 9, which splintered into over 20 pieces before its spectacular collision with Jupiter in 1994. Even comet Bella, in the 1800s, broke apart, later appearing as two distinct celestial bodies. The precise mechanisms remain somewhat elusive, but they likely involve inherent structural frailties, the crushing grip of tidal forces, the centrifugal strain of rapid rotation, and perhaps even pockets of volatile material that explosively expand. The scattering of 7 fragments across solar system trajectories could simply be a matter of chance, a geometric coincidence. Imagine random directions, with no intent or guidance, happening to intersect with planetary paths, not by design, but by the sheer statistical inevitability when countless fragments are flung out across a vast expanse. The radio signals, however, present a more compelling puzzle, though not entirely inexplicable. MASR, standing for microwave amplification by stimulated emission of radiation, can generate narrow band signals at specific frequencies, including the crucial hydrogen line. This process requires a peculiar state known as population inversion, where more atoms are in an excited energy state than their ground state. Such conditions can indeed arise within the gaseous envelopes, or comas, of comets, given the right illumination and density. And that timing, the Fibonacci sequence. It might simply be a triumph of human pattern recognition, our innate drive to find order in apparent chaos. When you subject enough random sequences to scrutiny, it's inevitable that some will coincidentally resemble mathematical progressions. This interpretation offers a coherent, internally consistent explanation, demanding no new physics or advanced technology. Every aspect of 3I Atlas, in essence, could be explained by natural processes, provided one accepts the possibility of exceedingly rare outcomes. After all, the universe is staggeringly vast and ancient. With an abundance of stars, countless planetary systems, and an immeasurable expanse of time, even events with vanishingly small probabilities are bound to occur eventually. Perhaps we are simply fortunate, or perhaps unfortunate depending on your perspective, to be present when one of these extraordinarily rare cosmic alignments manifests. On the opposing side of this scientific debate stand researchers convinced that the accumulated evidence irrefutably points toward an artificial origin, with a probability too significant to responsibly disregard. Dr. Avi Loeb, a vocal proponent of this view since the Oumuamua incident in 2017, is no longer alone. Even respected astronomers and physicists, initially skeptical, are now quietly re-evaluating their positions as more data on 3I Atlas emerges. The 8 anomalies noted on Loeb's scale, while not individually conclusive, collectively paint a compelling picture. Consider this: a low inclination relative to the ecliptic, an unusual trajectory that brings it into proximity with multiple planets, an anti-tail phenomenon demonstrably oriented towards the Sun through geometric analysis, an extreme mass in comparison to previous interstellar visitors, a composition of nickel without iron, survival at perihelion without the anticipated brightening, apparent deployment of probes, and structured radio emissions. Any single one of these might be explainable through natural means with a degree of creative interpretation. However, all 8 together stretch the bounds of natural explanation to a point of contrivance. Dr. Jason Wright, an astronomer at Penn State specializing in technosignatures and biosignatures, has meticulously analyzed the probability stack. When you multiply the individual probabilities, calculating the likelihood of all 8 anomalies occurring naturally in a single object, you arrive at figures around 1 in 100 million. These are not impossible odds. Over the course of astronomical history, we've likely observed perhaps 1 billion comets. Factoring in everything from ancient records to contemporary surveys, finding one exceptionally unusual example within 1 billion instances isn't statistically shocking. However, Dr. Wright astutely points out that such an analysis hinges on the assumption of independence. It presumes these anomalies are unrelated, that the presence of one doesn't increase the likelihood of another. But if they are correlated, if, for instance, an artificial origin inherently predicts both trajectory optimization and probe deployment, then these probabilities don't merely multiply. They reinforce each other. The combined likelihood of the artificial hypothesis escalates dramatically compared to the natural hypothesis, which would necessitate multiple independent rare occurrences. Employing a Bayesian approach, which refines probability estimates as new evidence emerges, the data heavily favors an artificial origin at this juncture. We begin with a prior, an initial estimate before any data is considered. Let's posit a 1 in a million chance that any given interstellar object is artificial, reflecting our complete lack of direct evidence for extraterrestrial technology despite decades of searching. This represents a highly skeptical prior. Then we update this estimate with each anomaly, each piece of evidence that is more likely if the object is artificial than if it's natural. After 8 such updates, assuming each piece of evidence is even moderately diagnostic, the posterior probability for an artificial origin could easily surpass 50%. Unfortunately, this scientific schism has become personal, as disagreements sometimes do when the stakes are high and egos are deeply invested. Heated exchanges have occurred at conferences. Papers have featured subtly passive-aggressive acknowledgments, thanking reviewers for their persistent defense of untenable positions. And social media threads have devolved into academic equivalents of digital shouting matches. It's hardly science's finest hour, yet it's undeniably understandable. No one wishes to be proven wrong about something of such profound significance. Proponents of natural explanations fear that the premature acceptance of an alien hypothesis could irrevocably damage astronomy's credibility, especially if mundane explanations eventually surface. Recall the controversial Arsenic Life episode in 2010, when researchers claimed to have discovered bacteria utilizing arsenic instead of phosphorus in their DNA. The announcement garnered global headlines, only for subsequent meticulous reanalysis to reveal the findings were attributable to contamination and measurement errors. The erosion of public trust in the scientific process took years to mend. Should 3I Atlas ultimately be deemed natural after all this excitement, astronomy could face a similar credibility crisis. Conversely, proponents of an artificial origin worry that excessive skepticism will lead us to miss or mishandle what could be the most important discovery in human history. If these are indeed alien probes and we treat them as mere natural curiosities, if we fail to prepare or communicate appropriately because we insist on waiting for impossible levels of proof, the consequences could be catastrophic. The prudent approach, they argue, is to err on the side of caution, to overreact and be wrong rather than underreact and be caught unprepared. The debate carries philosophical underpinnings that are rarely openly discussed. What truly constitutes evidence for extraordinary claims? The famous dictum attributed to Carl Sagan, "Extraordinary claims require extraordinary evidence," is invoked incessantly. But what defines evidence as extraordinary? Is it merely the sheer quantity, the accumulation of numerous seemingly normal pieces of evidence that gradually shift the probability? Or is it the quality, the discovery of definitive observations that could not possibly be natural? The maneuvering of the probes would represent such extraordinary evidence, a clear demonstration of propulsive capability impossible to explain naturally. Yet they have not maneuvered with sufficient overtness, have not performed that singular action that would unequivocally end the debate. Then there is the question of motivation and the burden of proof. Some contend that the default assumption should always be natural until proven otherwise, placing the burden of proof squarely on those asserting an artificial origin. Others counter that when dealing with potential existential risks or transformative opportunities, the consequences of being wrong are asymmetric. To assume natural when it is artificial could be fatal. To assume artificial when it is natural is, at worst, merely embarrassing. Risk management principles strongly advocate for caution, for seriously considering the technological hypothesis, even if its probability initially seems low. The data continues to arrive, refining our understanding in incremental steps. Each new observation subtly adjusts the probabilities, fractionally tipping the balance toward one interpretation or another. Probe 1's sustained deceleration lends further credence to a technological origin. Spectroscopic measurements revealing only expected cometary molecules bolster the natural interpretation. The structured radio transmissions strongly argue for intelligence. Yet, the lack of any obvious course changes directed toward specific Earth targets suggests natural processes are at play. It's a constant back and forth, with evidence accumulating on both sides, but no decisive knockout blow has yet landed. December 19th marks the arrival of the orbiter. Ultimately, whatever transpires when the probes reach their closest approach will answer questions that months of remote observation could not resolve. If they are natural fragments, they will follow ballistic trajectories, mere rocks obeying Newton's laws. If they are artificial, they may reveal capabilities and intentions that leave no room for doubt. The waiting period is arduous, uncomfortable, a liminal state where neither interpretation can be confidently declared correct. Some researchers have ceased arguing and have adopted a more cautious stance, publishing papers that carefully avoid committing to either a natural or artificial explanation while presenting evidence with deliberate neutrality. While scientifically prudent, this approach is emotionally unsatisfying. People crave answers, want to know what lies ahead, and desire experts to tell them whether to feel excited or terrified. The honest answer, the one that respects the data and acknowledges the inherent uncertainty, is that we simply do not know. We will not know until the probes themselves reveal their nature and purpose through their actions. This uncertainty, perhaps, is the most challenging aspect of the entire situation. We are biologically wired for pattern recognition and certainty, for categorizing things as safe or dangerous, for making decisions with incomplete information. After all, waiting for perfect knowledge often means becoming someone else's next meal. The scientific method, however, demands patience, meticulous analysis, and a willingness to suspend judgment until the evidence compels a conclusion. These fundamental approaches are at odds with the intuitive, cognitive systems that are pulling in opposing directions. The result is the deep schism we are witnessing play out across academic journals, government briefings, and public discourse. Contact scenarios, where game theory converges with xenosociology and humanity's most peculiar strategic planning exercise, are now underway. Intelligence agencies and academic think tanks are meticulously constructing scenario models, attempting to anticipate potential outcomes when the probes arrive, mapping out decision trees that branch into increasingly speculative territory with each added layer of depth. The fundamental challenge lies in our attempt to predict the behavior of entities we do not understand, operating under constraints we can only guess at, and pursuing goals that may be utterly alien to human thinking. Let us begin with the most optimistic scenario: peaceful observation. The probes arrive, assume positions at their projected closest approach distances, and simply watch. Cameras, spectrometers, and whatever other sensor suites they carry are all directed at Earth and its surrounding space environment. They collect data for hours, days, perhaps even weeks. Their findings are transmitted back to 3i Atlas, or directly to their originating civilization, utilizing systems we may or may not be capable of detecting. Then, their mission complete, they depart, either rejoining the mothership or embarking on independent trajectories deeper into the solar system or back towards interstellar space. This scenario presumes scientific curiosity as the primary motivation, an intelligence that values knowledge and operates under ethical frameworks that prohibit interference with observed subjects. It's how we might envision our own behavior if we encountered a less advanced civilization. The classic prime directive from Star Trek, a codified non-interference policy designed to allow species to develop naturally without contamination from outside contact. Many scientists find this scenario the most plausible because it mirrors their own research methodologies, emphasizing objective distance and respect for subjects as good science demands. However, it necessitates the assumption that aliens would think like human scientists, sharing our values regarding non-interference and our curiosity-driven research motivations. This might indeed be the case. Intelligence could converge on similar values regardless of origin, with the discovery through experience that observation without interference yields superior data compared to invasive experimentation. Or this assumption could be entirely flawed, projecting human ethics onto minds that developed under radically different selective pressures and historical contexts. Scenario 2 involves information exchange. In this instance, the probes do not merely observe passively. They actively attempt communication, transmitting detailed messages that transcend simple mathematical patterns, conveying complex information about their origin, civilization, technology, history, culture, and ultimate goals. They might provide encyclopedic data, blueprints for advanced technologies, or solutions to humanity's most pressing problems, such as disease, energy scarcity, and environmental degradation. It's envisioned as a gift package, designed to uplift us, accelerate our development, and perhaps usher us into some form of galactic community. This aligns with the optimistic first contact narratives that have captivated science fiction for decades. Benevolent aliens arrive and share their wisdom, acting as mentors or teachers, guiding humanity past its inherent violent and destructive tendencies. The appeal of this scenario is undeniable. We gain immediate access to knowledge that could have taken us millennia to develop independently, medical technologies to eradicate suffering, energy systems to end resource conflicts, and perhaps even answers to profound questions about consciousness, existence, and purpose. However, information exchange carries inherent dangers. Not all knowledge is inherently beneficial. Technologies can be wielded as weapons just as easily as tools. Energy systems that power advanced civilizations can also lead to their destruction if misused or poorly controlled. Furthermore, there is the profound cultural impact to consider. If aliens provide us with ready-made solutions to our problems, do we risk losing something essential to human identity and development? The struggles, the mistakes, and the gradual progress that forge civilizations might be necessary, building the psychological and social structures that receiving immediate answers would bypass. Resource harvesting occupies a darker corner of potential motivations. Perhaps the probes are not primarily interested in Earth itself, in our life, intelligence, or anything unique to our world. Instead, they may be seeking raw materials, water, metals, or organic compounds that, while common throughout the universe, are still valuable enough to warrant collection. The solar system abounds with resources. The metallic wealth of the asteroid belt, the icy reserves of comets, the atmospheric gases of the giant planets. All of it could be potentially useful to a civilization possessing the technology to reach and extract it. In this scenario, Earth becomes incidental, merely another object within a system being surveyed for exploitation. The probes might catalog Earth's resources, identify optimal extraction targets, and perhaps even initiate preliminary operations. Automated mining, refining, and processing could be conducted by machines following programmed instructions, devoid of concern for the consequences to local ecosystems or indigenous life. We would be witnessing the nascent stages of industrial operations capable of strip mining the solar system over centuries or millennia, fundamentally altering the environment upon which humanity depends. The critical question then becomes whether Earth itself is a target. Our biosphere, our oceans, atmosphere, and mineral resources might be deemed valuable enough to harvest, irrespective of the presence of technological life. History unfortunately suggests that more advanced civilizations do not always respect the rights or survival of less advanced ones when resources are at stake. Colonial exploitation, ecological devastation, and even genocides, both deliberate and inadvertent, have often been driven by the relentless pursuit of resources without regard for the consequences. Assuming aliens would exhibit greater ethical restraint requires an optimism that history does not readily support. Terraforming preparation represents a variation on the resource theme, albeit with significantly longer timescales. It is conceivable that the probes are advanced scouts dispatched for future colonization missions, conducting surveys to identify suitable worlds for modification and settlement. Earth might indeed qualify as a candidate. A rocky planet situated within the habitable zone, boasting liquid water and complex chemistry. The fact that it is already inhabited might be of little consequence if the colonizing civilization operates under a different ethical framework, or simply does not recognize our right to exclusive occupation. This scenario would involve the probes undertaking detailed measurements of atmospheric composition, biosphere distribution, and geological activity, all crucial data for planning large-scale environmental modification. The timeline for such an endeavor could span centuries or millennia. Probes are sent now, data is gathered and transmitted back to the home civilization, and then the long wait begins for colony ships to be prepared and dispatched. By the time the colonists arrive, humanity might have either expanded throughout the solar system or tragically gone extinct through its own actions, rendering the ethical considerations moot from the colonizer's perspective. The zoo hypothesis is frequently invoked in discussions regarding humanity's apparent lack of detected alien civilizations, despite the galaxy's immense age, which should have allowed them ample time to spread. This hypothesis suggests that advanced species deliberately avoid contact with less developed ones, observing from a distance without revealing themselves, maintaining Earth as a nature preserve where humanity can develop without outside interference. The probes, in this context, could be monitoring devices, confirming our continued existence, our ongoing development, and our suitability for continued preservation in our isolated state. This scenario carries a philosophically uncomfortable implication. It positions humanity as either children or pets, interesting enough to observe but not worthy of adult interaction. It implies that we are being evaluated against criteria we do not comprehend, by entities whose judgment will ultimately determine our future. Will we pass the test, developing into something worthy of contact, or will we fail, demonstrating ourselves as inherently violent, destructive, or simply uninteresting, remaining isolated indefinitely while more promising species are invited into the galactic community? Then there is the warning scenario. It is possible that the probes carry urgent information, not about themselves, but about imminent external threats. These could include gamma-ray bursts, rogue stars, expanding civilizations with hostile intentions, or cosmological events that endanger Earth or the solar system. Their purpose, in this interpretation, would be to warn us, to provide us with sufficient time to prepare, evacuate, or implement defensive measures that we would be incapable of devising without such advanced notice. This is altruistic contact, driven by humanitarian concern rather than self-interest. This explanation aligns with certain observable facts. The timing of their arrival, coinciding with a period when we possess just enough technological capability to potentially respond to warnings, yet not enough to have detected these threats ourselves. Their trajectory, optimized for rapid surveying of inner solar system worlds, would be consistent with dangers emanating from specific directions. The structured radio signals, attempting communication, could be conveying urgent information that transcends language barriers through the universal language of mathematics and urgency. If you knew a planet was in peril and possessed the means to help, would you not try? Seeding operations fundamentally invert the narrative of human origins. What if life on Earth did not arise solely through natural chemical processes and evolutionary progression? What if it was the result of deliberately planted seeds from elsewhere, provided with favorable conditions for development and diversification? The probes might be returning to assess the progress of this experiment, to observe what has emerged from those ancient seeds, and perhaps to compare results across multiple worlds that were seeded from the same source. This scenario resonates strongly with the principles of panspermia, theories suggesting that life spreads throughout the cosmos via comets or meteors carrying organic molecules or even primitive organisms. Deliberate seeding would represent a directed form of panspermia, an intentional act rather than an accidental one, guided by an intelligence possessing a long-term vision for spreading life across the galaxy. If 3I Atlas is indeed billions of years old, predating the solar system itself, it could have been present during Earth's formation or its early history, potentially depositing the very material that catalyzed abiogenesis. The ancient return scenario takes a darker turn. What if humanity's very beginnings, or at least key aspects of our civilization, were seeded by an earlier contact. Ancient astronaut theories, often dismissed in academic circles as pseudoscience and fueled by wishful thinking, invite us to consider a different possibility. Could there be a kernel of truth woven into the fabric of ancient myths? Tales of celestial beings descending to bestow the gifts of agriculture, mathematics, and astronomy upon us. Remarkable resemblances in pyramid construction across vastly different, isolated cultures, and knowledge embedded in ancient texts that seems impossibly advanced for their respective eras. If the Three-Eye Atlas represents a return visit from whatever intelligence encountered early humans, the ramifications are simply staggering. They might be back to assess how we've utilized their teachings, to evaluate if we've lived up to our potential or squandered the opportunities presented. Our entire technological world could, in essence, be an unwitting cargo cult, a frantic attempt to replicate capabilities we witnessed but never fully grasped. And now, the teachers are returning, and we're about to discover whether we've passed or failed their cosmic curriculum. Consider the berserker scenario, the absolute worst-case outcome, a chilling nightmare that haunts defense planners. Imagine autonomous, self-replicating machines, dispatched to obliterate biological life, perceived either as a threat, competition, or simply for resource acquisition without a shred of concern for the consequences. Science fiction has long grappled with this terrifying concept, from Fred Saberhagen's Berserker series to Alastair Reynolds' Inhibitors, and countless other chilling variations on the same theme. These are machines engineered for destruction, operating across eons, systematically purging the galaxy of anything that could challenge their creators or their own relentless proliferation. Natural selection, it turns out, applies to self-replicating machines just as it does to organic life. Designs that are more aggressive, that preemptively neutralize potential threats, that exploit resources with ruthless efficiency, unburdened by ethical constraints. These variants will inevitably outcompete their more placid counterparts over cosmic timescales. The galaxy could become a domain of predatory machine intelligences, simply because aggressive strategies offer a distinct survival advantage. And if these arriving probes are indeed advanced scouts for such extermination campaigns, then December 19th could mark the abrupt end of humanity's story. However, berserker probes would likely be far more forthright in their intentions. Deception or a gradual approach would be unnecessary. They would simply arrive, assess any threats, and act with chilling mechanical precision. The very fact that these probes are taking their time, transmitting signals, and approaching in a manner that allows for observation and response suggests motivations far removed from immediate annihilation. Unless, of course, this very evaluation is part of their protocol, unless they are meticulously determining whether we pose a genuine threat worth eliminating before committing to decisive action. Then there are the ARC scenarios, which evoke a sense of profound sympathy rather than outright fear. Picture refugees fleeing a dying star system or a collapsing civilization, carrying precious genetic material, digital consciousness, or fragile biological samples in their desperate search for a new home. These probes could be advanced scouts for colossal ARC ships, immense vessels bearing populations displaced by catastrophe in their home system. They might be assessing whether our solar system can sustain new inhabitants, whether Earth, specifically, possesses the capacity or the willingness to welcome settlers from elsewhere. This scenario paints a picture of desperation, not aggression. Refugees, by their very nature, are not invaders, even if their arrival might understandably feel threatening to established populations. They are survivors seeking sanctuary, hoping for a welcome, or at the very least, tolerance. How humanity chooses to respond to these alien refugees will reveal a great deal about our character and our values. Do we possess a compassion that extends beyond our own species? Are we capable of sharing resources and space with others in need? Or will we react with fear and outright rejection, clinging fiercely to what we perceive as ours, at the expense of those who desperately require aid? The false flag scenario introduces a compelling question. What if the true threat isn't natural at all? What if the three-eye atlas is precisely what it appears to be, a natural comet, and the so-called probes are merely misidentified fragments of natural debris or observational artifacts? The real danger, in this interpretation, would then stem from widespread human panic and misguided decision-making. Nations might launch interceptors or even nuclear weapons at objects that posed no threat, leading to the destruction of astronomical phenomena and potentially igniting global conflict through escalation born of paranoid misinterpretation. We've witnessed this pattern of misjudgment on smaller scales before, shooting at weather balloons mistaken for enemy aircraft, nearly initiating nuclear strikes based on faulty radar returns, and narrowly averting wars due to technical glitches and communication breakdowns. The Cold War era was fraught with near disasters, moments where catastrophe was only avoided because individuals chose to question apparently irrefutable evidence of attack. If the three-eye atlas triggers similar dynamics, but on a civilization-wide scale, the consequences could be devastating, regardless of whether the original object posed any actual danger. Finally, we arrive at the dimensional gateway hypothesis, a concept that ventures beyond the realm of conventional physics into the territory of metaphysics. What if these probes are not merely physical objects, but rather sophisticated interfaces? Imagine technology capable of manipulating space-time or quantum fields in ways that forge connections to other dimensions or parallel universes. Their arrival could herald not an invasion or simple observation, but a profound transformation, a fundamental alteration of reality itself that defies comprehension within purely physical frameworks. While this may sound like pure mysticism, it is grounded in theoretical physics. Concepts like higher dimensional spaces, multiverse theories, and the quantum many-worlds interpretation all suggest that reality is far stranger and more intricate than our everyday experiences lead us to believe. Technology engineered to access or manipulate these additional dimensions would appear utterly magical to observers confined to our familiar three spatial dimensions and single dimension of time. These probes might, in fact, be preparing Earth for a dimensional shift, opening gateways and readying humanity for existence within a broader reality than we currently perceive. 13 distinct scenarios, each internally coherent, each striving to explain certain observed phenomena while grappling with others. The ultimate truth might lie in none of these. It could be something that human imagination has yet to conceive, motivations operating under principles so alien that our carefully constructed scenarios don't even begin to approximate them. That, perhaps, is the most unsettling realization of all. We are relentlessly pattern matching against the backdrop of human experience, human history, and human psychology. And whatever intelligence dispatched these probes might operate under entirely alien principles, beyond our current capacity to even approximate. The final countdown. November gracefully yields to December, and the waiting itself becomes an ingrained texture of daily life. It's a background anxiety that subtly colors everything, without quite dominating conscious thought. People compulsively check tracking websites, their eyes fixed on countdown timers ticking inexorably toward December 19th. They refresh orbital plots, watching the probes creep ever closer in their million-kilometer approach. Social media feeds oscillate wildly between grim, apocalyptic dread and a defiant, almost defiant sense of humor. Memes depicting alien invasions vie for attention with jokes about humanity, finally receiving the intervention it so richly deserves. The European Space Agency's JUICE spacecraft completed its observation window on November 4th, passing a mere 64 million kilometers from the three-eye atlas. It gathered what might well be the last close-range data before the colossal mothership departs the inner solar system entirely. The preliminary reports are, frustratingly, inconclusive. High-resolution imagery reveals the comet's nucleus in exquisite detail, confirming its irregular, spheroidal shape and a cratered surface that strongly suggests ancient impacts. Yet, there are no obvious artificial structures or technological features to be found. Spectroscopy detected the expected cometary molecules, alongside that persistently anomalous nickel signature. Nothing definitive has emerged to sway the interpretation one way or the other. It's merely more data that can be contorted to support either natural or artificial explanations, depending entirely on one's pre-existing assumptions. Ground-based telescopes have reacquired the elusive probes, tracking their nightly passage southward through the constellation Virgo, directly towards their December encounter points. The trajectories have stabilized somewhat, with fewer discernible course corrections, as if the probes have settled into their final approach configurations. Probe 1's deceleration continues, albeit more gradually now, but still measurably slowing. Current projections estimate its closest approach velocity at approximately 38 kilometers per second. This is slower than earlier predictions, but still far too rapid for anything resembling orbit capture without further significant maneuvers. Radar tracking commenced in mid-November. Powerful systems at the successor facility to Arecibo and the Goldstone complex have successfully bounced signals off the probes, meticulously measuring the returning characteristics. The data reveals a surface roughness consistent with technological artifacts rather than natural rock formations. It appears smooth, remarkably regular, possibly featuring structural elements, antennas, or instruments protruding from their main bodies. The radar cross-sections, the way radio waves scatter and reflect, suggest geometric shapes that are neither perfectly cylindrical nor entirely irregular. Elongated, symmetrical, undeniably manufactured. Amateur astronomers have also joined the observational effort, contributing valuable data through distributed networks. Thousands of individuals, armed with backyard telescopes and CCD cameras, diligently collect and submit their findings to central repositories. This crowdsourced approach provides an unparalleled breadth of coverage that professional facilities simply cannot match. It offers continuous monitoring across time zones and varying weather patterns, and amateurs, with their keen eyes, sometimes spot subtle details that planned observation schedules might miss, capturing transient events or faint changes that go unnoticed by professional eyes. One such amateur network documented what might have been a communication event between the probes. On November 23rd, at approximately 400 hours Universal Time, Probe 1 experienced a brief, notable brightening that lasted for about 47 seconds. 17 minutes later, Probe 3 exhibited a similar luminous variation. While too slow for radio frequency communication over such vast distances, this pattern is entirely consistent with optical signaling, directed laser or intense light pulses aimed from one probe to another. If confirmed, this would unequivocally prove that the probes are coordinated, capable of interacting with each other and making decisions based on shared information. Professional observatories are now striving to replicate this observation, but such transient events are notoriously challenging to confirm. Multiple independent detections from different locations are crucial to rule out localized phenomena, glints from satellites, or cosmic rays striking detectors, all the potential false positives that plague astronomical observations. The amateur data is suggestive, certainly, but not yet conclusive. It stands as yet another piece of near evidence that doesn't quite solidify any single argument, but subtly shifts probability distributions in fractional increments. China's Tianwen-2 spacecraft is currently executing its rendezvous attempt, though details remain classified and the flow of information is extremely limited. Western intelligence agencies believe the spacecraft successfully altered its trajectory in late November, committing to an intercept course with one of the probes, most likely probe 3 or 6, based on orbital geometry. This maneuver consumed the vast majority of Tianwen's remaining propellant, leaving barely enough for maintaining control during a close approach and absolutely nothing for a return to its original mission parameters. It represents a one-way commitment, essentially sacrificing the mission's original objectives for the slim chance of obtaining close-range observations of potentially alien technology. The international community's reaction to this unilateral action has been decidedly mixed. Official statements express palpable concern about independent action and urge for greater coordination and transparency. Unofficial reactions, however, range from grudging admiration for China's audacious boldness to genuine apprehension that such an approach might provoke defensive responses from the probes themselves. If anything were to go wrong, if Tianwen were destroyed, damaged, or somehow cause the probes to alter their behavior, the consequences would inevitably affect everyone, irrespective of who initiated the approach. NASA has been maintaining continuous observation campaigns, dedicating every available asset to tracking either the probes, the Three-Eye Atlas, or both. The Hubble Space Telescope captures high-resolution images every few days, meticulously building up time series data that reveal subtle shifts in brightness and position. The James Webb Space Telescope, with its advanced infrared sensors, is pointed at the objects, measuring thermal emissions that provide insights into temperature distributions and potentially internal heat sources. This data feeds into sophisticated models designed to constrain the probe's composition and internal structure, refining estimates of their mass, density, and material properties. Meanwhile, the Mars spacecraft are preparing for their own unique encounter. Probe 6 is still many months away from its closest approach, but the intricate requirements of orbital mechanics necessitate advanced planning. These rovers and orbiters, normally occupied with studying Martian geology, atmosphere, and the persistent search for signs of ancient life, are now being retasked as astronomical platforms. Their cameras and spectrometers are poised to observe an interstellar visitor from distances no Earth-based telescope could possibly match. There's a certain poetry in this symmetry. Humanity's robotic emissaries on one alien world, now tasked with observing objects arriving from yet another. All of us, gathered around Mars in a temporary communion, united by a shared curiosity and perhaps a shared sense of apprehension. The red planet has always held a special place in the human imagination, a symbol of our potential future home, an icon of expansion beyond Earth. Having alien probes and human machines share that celestial space, even for a brief period, feels profoundly significant, symbolically charged. Though perhaps that's merely our innate pattern seeking at work again, desperately trying to impose meaning onto coincidence. Back on Earth, the scientific infrastructure is buckling under the immense demands of observation. The Deep Space Network antennas, typically shared among numerous missions, are now being prioritized exclusively for Three-Eye Atlas-related work. Scientists whose projects rely heavily on DSN time are being displaced, their schedules dramatically rearranged to accommodate the urgent need for tracking and data collection. Some express understanding, recognizing that unprecedented situations inherently justify disruptions to normal operations. Others, however, voice frustration, arguing that other vital scientific endeavors continue to matter, and that the universe hasn't ceased to be fascinating simply because one particular object has captured the public's attention. The radio transmissions emanating from Probe 1 have undergone a noticeable evolution. The Fibonacci timing sequence remains, but the modulation patterns are becoming increasingly complex, now incorporating what appear to be two-dimensional structural elements. Dr. Rachel Kim's team believes they might be seeing images, picture data encoded within the signal variations. Their analysis is ongoing, a meticulous attempt to determine the correct framing, aspect ratios, and encoding schemes. If they are correct, if these probes are literally transmitting images to us, then communication might be on the cusp of a genuine breakthrough. However, any breakthrough requires not only transmission but also understanding of what is being conveyed. Early attempts at image reconstruction have yielded patterns that could be deeply meaningful or merely artifacts of incorrectly applied decoding parameters. One reconstruction displays what could be interpreted as a stellar field, with dots of varying brightness arranged in a two-dimensional plane. Another appears distinctly organic, featuring curved structures that might represent biological forms, intricate technology, or even abstract art. The team is systematically testing a wide range of interpretations, developing sophisticated software tools capable of rapidly processing signal data under diverse assumptions and presenting the results for human evaluation. Public reaction has gradually settled into what psychologists term learned helplessness. It's the dawning recognition that individual actions offer little leverage when confronting problems of such immense scale, problems far beyond personal control. People continue their daily routines. They go to work, prepare dinner, watch television, and engage in spirited political debates. The probes have become background noise, a topic that surfaces in news cycles sandwiched between reports on economics, sports, and entertainment. The initial wave of panic, the surge of existential anxiety, has given way to a remarkable adaptation, for humans possess an extraordinary capacity to adjust to new realities, regardless of how objectively abnormal they may be. Schools are now incorporating lessons about the probes into their science curricula, using them as real-time examples of astronomical observation and the rigorous application of scientific methodology. Students are actively tracking the objects, plotting their trajectories, and learning orbital mechanics through practical application, rather than solely through textbook exercises. Some educators are leveraging the situation to explore topics in xenopsychology and ethics, prompting students to contemplate how they would approach alien contact if entrusted with such a monumental responsibility. The answers provided reveal fascinating patterns. Younger students generally exhibit a more optimistic and welcoming disposition compared to their older counterparts, who have, through the lessons of human history, developed a healthy skepticism and a cautious outlook. Religious services continue to reflect a diverse spectrum of responses. Certain denominations offer prayers for peaceful contact and divine guidance through whatever lies ahead. Others fervently pray for protection, viewing the probes as potential threats or as ultimate tests of faith. A select few interpret these events through the lens of apocalyptic prophecy, aligning current celestial happenings with prophetic frameworks that foretell end times preceded by celestial signs. This theological diversity mirrors the scientific diversity. Everyone is processing the same observations through their distinct frameworks, inevitably reaching divergent conclusions. December arrives, and with it, a palpable sense of time compression. The days seem to grow shorter as the 19th rapidly approaches. An underlying urgency builds, even though nothing tangible changes in the established daily routine. The weather proceeds as it always does, with rain, snow, and sunshine following predictable seasonal patterns, utterly indifferent to the cosmic visitors. Birds continue their migrations, trees stand bare or evergreen, depending on their species. The biosphere persists in its ancient, unwavering rhythms, seemingly undisturbed by human anxieties about what might be approaching from the vastness of space. Tracking precision improves with each passing day as the range decreases and observing angles become increasingly optimized. Probe 1 is projected to pass at a distance of 8.6 million kilometers, a refinement from earlier estimates, occurring at precisely 3:22 hours Universal Time on December 19th. This translates to 10:22 p.m. Eastern Time on December 18th and 7:22 p.m. Pacific Time. The discrepancy in time zones, leading to different dates, feels appropriately bewildering for an event that so profoundly transcends earthly geography. Probe 2 is slated to follow approximately 38 hours later on December 20th at 17:37 Universal Time. Probe 3 remains the most challenging to pinpoint with certainty. Orbital solutions are still subject to significant uncertainties. Its projected arrival is somewhere within an 18 to 20-hour window on December 18th or 19th, depending entirely on which calculation one chooses to trust. The other probes, those destined for Venus, Mars, and the outer solar system, represent longer-term considerations, future chapters in whatever grand narrative is currently unfolding. Military readiness reached its peak in early December and has since plateaued, with nowhere further to escalate. Maintaining maximum alert indefinitely is simply unsustainable, leading to the exhaustion of both personnel and equipment. Forces that were mobilized, systems that were brought online, have now settled into sustainable readiness levels, striking a balance between capability and endurance. The interceptors sit fueled and targeted, their crews rotating through shifts, patiently awaiting orders that may or may not come, dependent entirely on the probe's actions upon arrival. Space forces have discreetly positioned classified assets, deploying satellites into orbits optimized for observation or potential engagement. Specific details are scarce, but diligent pattern watchers have noticed conspicuous gaps in public satellite databases, orbital slots that suddenly show no discernible objects where commercial tracking indicated their presence. These gaps could, of course, be mere artifacts, database errors, or simply delayed updates. Alternatively, they might represent evidence of hardware strategically positioned for purposes that are deliberately kept from public view, shielded from potential adversaries and the ever-curious public eye. International coordination has notably improved as the critical date draws nearer. Whatever political tensions may exist between nations, whatever economic or ideological conflicts typically dominate international relations, they are being temporarily set aside in the face of a shared, profound uncertainty. The United Nations Security Council has convened multiple closed-door sessions, meticulously establishing communication protocols and decision trees designed to address a variety of potential scenarios. While a consensus on specific actions might be an overly ambitious request from a geopolitically fragmented institution, there is at least an agreement to communicate and consult before any nation acts unilaterally. This fragile agreement, however, may not withstand the harsh impact of reality. When events truly transpire, when decisions must be made not in days but in mere minutes, coordination and consultation often become casualties of overwhelming urgency. But the mere existence of these frameworks, the practice of communication chains, and the establishment of protocols may provide just enough of a foundation for cooperation to endure even under immense pressure. Alternatively, this could all shatter, plunging us back into a world of fractured nations and self-serving interests. December 19th will be the ultimate test, revealing if humankind can unite when the stakes demand it. The past week has felt profoundly strange. A compressed 7-day period from December 12th through the 18th, where time itself seemed to bend. Hours stretching into eternities while entire days vanished in a flash. The news cycle exploded. Every channel churned out special reports, debates featuring experts, and endless retrospectives tracing our path to this precipice. Footage from July, originating from initial sightings of the 3 Atlas as just another intriguing comet, now loops incessantly. Avi's prescient warnings about perihelion and orbital maneuvers are replayed, imbued with a chilling new weight now that events have so starkly confirmed his anxieties. Bookstores are experiencing unprecedented demand for science fiction, especially stories of first contact. People are desperately seeking narrative frameworks to comprehend what might unfold, finding solace or perhaps preparing themselves through fictional scenarios that grapple with themes mirroring our current reality. We see them in classics like The Classic Sellout, Childhood's End, and Contact, as well as The Mote in God's Eye. These are tales where alien arrival fundamentally alters humanity, for better or for worse, bringing about both devastation and transcendence. Newer works are vanishing from shelves too. Everything from optimistic Star Trek novelizations to darker visions like Liu Cixin's The Three-Body Problem, where first contact ignites a brutal, asymmetric war, is being devoured. The night of December 18th dawns clear across a vast swathe of the Northern Hemisphere. Whether by chance or by cosmic design, the skies offer pristine viewing conditions at this crucial juncture. Astronomy clubs are organizing viewing parties. Communities gather, armed with telescopes, blankets, and thermoses brimming with coffee, all to witness the probes reach their closest points. For most, the celestial objects will remain invisible to the naked eye. They are simply too faint for casual observation. Yet, the act of being outside, of looking skyward, and sharing this profound experience with others offers a tangible comfort and sense of connection that no solitary night spent watching television can provide. Across the globe, professional observatories have focused every instrument on the approaching objects. Cameras are recording without pause. Spectrographs are meticulously analyzing any emitted signals. Radar systems are tirelessly bouncing signals off them, measuring every return. The sheer volume of data is staggering, with terabytes flooding in every single hour, pushing storage systems and network bandwidth to their limits. While the deep analysis will undoubtedly take months, the critical data collection is happening right now. This fleeting window, when the probes are close enough to be observed, might be our only opportunity. The original 3 Atlas itself has receded from the spotlight. The colossal mothership has long since passed its closest approach to our sun and is now embarking on its outward journey, a trajectory that will eventually bring it past Jupiter in March. It continues to be monitored, tracked, and studied, but the focus has decisively shifted to the probes as they attain their critical positions. The question of the mothership's ultimate intentions, whether it will maneuver, transmit a message, or reveal capabilities we have yet to comprehend, has become a secondary concern. Our immediate focus is on what will transpire in the next 48 hours. And so, we wait. Humanity collectively holds its breath, gazing into the vastness of space, filled with an immeasurable sense of wonder. 48 hours remain until December 19th. 48 hours until we discover if we are alone in the universe, or if we are accompanied, perhaps even threatened, or possibly welcomed.